Hi, I'm Marcel, and I have an idea for a new programming language, which is kind of unfortunate because I already created a language, which I'm now using daily and writing my master's thesis about it. So, having this idea for yet another language means that it's kind of hard to focus on other stuff. So, I'm allowing myself to work on this for just like 1 day a week, maybe. And that's actually what these videos are about. So there's some way to hold myself accountable to only work on this a limited amount of time. Because, if I work on this just a little bit in the rest of the week, then I can't make these videos because I want to document everything I do on these videos. These won't be like polished, planned out things. This will just be development sessions. Right. So let me see, I have some notes here. What I wanted to talk about. Share my screen. Perfect. Yeah, that's basically why I want to stream or make videos, or why publish basically. To hold myself accountable. And also I looked at YouTube and it doesn't seem like there are good series of let's develop a programming language together kind of videos. There are some of them, but they are mostly limited in scope. It's like a few weeks, mainly focused on these are the concepts you need to understand when developing a language, but less of creating like a real usable language. Usually it's like we developed this for a few weeks maybe, and now let's put it on the shelf and never touch it again and move on to the next project idea, which is kind of unfortunate, I think. So this will be more like a long-term toy hobby project maybe. Yeah. And before talking about what makes the language unique and interesting, I want to have a quick note about the name. So choosing names is pretty difficult for programming languages. There are so many languages. Yeah, and in the end I settled on Kamin, which is basically fireplace in German. To be honest, I just wanted it to sound kind of cozy, and I didn't spend too much time thinking about it, like 5 minutes. I gave myself 5 minutes, and that's what I came up with. Yeah, there doesn't seem to be a language named that already, so I think we're good to use that. And to understand why why the language is the way that it is, I want to share 2 languages that have a kind of big impact on this language. And the first of them is Rock, which is a functional language. So this is also going to be a functional language. In this case, meaning that data structures are immutable. You can't have any cycles or something like that in your data. And functions, you can't modify data. Yeah, so immutable and acyclic. Which means, for example, a list append function wouldn't like take a list and mutate it, but it would take a list and an item and return a new list. In many cases, this can be optimized under the hood to modify the list, but in some cases not. So the semantics of the language are totally immutable, pure functional. Yeah, I'm also hoping this language will be fast, mainly because I try to infer types. So this will be a statically typed language, which means that a variable can't hold a value of some type at some point in time and then later on store a value of another type. That doesn't work for variables. The types have to be known just by looking at the code, just by at compile time basically. Right, and that's actually a cool thing about Rock, that you don't have to write a single type. Everything is inferred. For example, if we have this right here, you see this is, okay, the type is a fraction. And there are these things called tags, which are just uppercase symbols, I guess, like foo, for example. And you can see that this is similar to, if you just write for. this is like a compiler special thing that the language understands. And false a number, foo is a foo. So this is basically like an identifier or symbol or tag or whatever it's called. And you can basically do nothing with this except compare it with other symbols. So, numbers, you can add them, you can subtract them, you can print them, but this you can only compare if it's equal to another tag. But what's cool is that, for example, true and false, they are really just some tags. Yeah. And if you have a function, functions are written like this. So we have a function foo. So foo is a function that takes an n. You do that with this weird backslash. And then you can check if, for example, n is 0, then we want to return foo, otherwise bar. And this is a function that takes a num and returns, this brackets mean either this or that. So it either returns bar or foo. Yeah, I think they are just sorted alphabetically, but yeah, that's the whole idea. And let's see. The cool thing is about how types combine. So let's say you have a really complicated function that branches at some point, and then later on those branches are joined. For example, our function here with the that we had with the if. In one case returns foo, the other bar. Then the compiler will automatically see, okay, the type of this is foo, the type of this is bar, and then we can join types in some way. We can join the type foo and bar to the type foo or bar. So foo has this type, bar has this type but with bar inside, and they get joined to this. And that's really powerful because it allows you to have some kind of type safety. For example, if you have a struct in map or dictionary or object or whatever you call it in one branch and another one in another branch, they have to have the same fields. So you have some kind of type safety. Although, of course, this is, these are all structural types, which means they don't have names. They are just, they have the same structure, those values. That's basically everything that tells you. But types having the same structure is actually important to optimize the language, because then you can, you don't have to store metadata about what's the structure of the type. You can just store the data. And you can also decide at compile time how the data will be stored, what's the memory layout of the data, so that, at runtime you can just be really quick in accessing that. Yeah, and the other language that is an inspiration is Zig, which is a completely different language. You can see it looks a lot more C-like with curly braces and so on. The cool thing about Zig is that it supports comp time, which basically means executing arbitrary code at compile time. And this means that you don't need macros or anything like that. Instead, you can do anything at compile time. Let me pull up a blog post I recently wrote about that. Yeah, so in C or Rust or something, you have macros that work mostly on the syntax level, but which are entirely separate from the core language. And the compiler can optimize some parts of the core language as well. So these are all things that can run at compile time. In Zig, it's more like integrated into the language. So there's, for example, a type info, a type of function. If you have some value of an unknown type, which is something you can do in Zig, then you can ask what's the type of this value, and you get like an opaque type thingy. But then you can call type info on that, and that basically just returns an enum. It returns, is this a struct? Is this an int? So then when you have a function, for example, the print function internally uses this function to form types, then it can just say, well, I want to format any type. This is known at compile time when this function is called. and it just checks what's the type of this. Does this type have a format method inside? If so, then I use that. Otherwise, I call type info, and depending on what kind of type it is, I'm gonna choose a different formatting strategy. So then when you call this format type function with a bool and a custom type, for example, you actually get two different functions, because this function is basically recompiled for every type that you call it with. So you have one function that can format bools and one that can format users. And this, this in here is this is basically all the rest that couldn't be evaluated at compile time. So when you call format type with a bool, then it just says, well, t is just bool. At runtime, this doesn't exist. This is only, this is known at compile time. And bool doesn't have a format method, so this evaluates to false, which means that the thing inside the if isn't even type checked, which would actually be like a bad thing if it was, because bool.format doesn't exist. So yeah, this is just if false and then something, so this doesn't even get compiled, the part inside. Type info returns bool, so then only this branch here is compiled. And that's actually what you see in here, that this is the only remaining statement of the function. Yeah, and I want to do something similar, basically guarantee that whatever can be evaluated at compile time will be evaluated at compile time. Right, let's look back here. Okay, we have the inspirations, which are rock and zig. And now let's move on to the language idea. The ending will probably be, for now, okay, maybe I'll change it. Actually, maybe I'll even change the name, because it's kind of, well, anyways. So the idea is that you can just, declare variables like this, and you can use symbols like uppercase things like foo or bar or true or something. And these symbols can also have a payload, for example, like this. In general, if you define, well, I'll get back to that later. Yeah, you can define functions like this, perhaps with parameters in front of the equal sign, and then you can write something here, and this would basically call a function. Yeah. Right. And you can, I want this to be an indentation-based language, just because, my previous language is kind of more of a C-like language, so I want to do something different. Yeah, I'm gonna maybe indent with 2 spaces. And yeah, you can basically switch on, let's say this is a not function that accepts a bool, and no, you can't specify types in here. So you basically switch on this. If it's true, then you return false. If it's false, you return true. Something like this. And this would evaluate to false, this would evaluate to true, and this would raise a compiler error, because this would try to compile not for ints, and you can't switch on ints. Right. Okay, yeah. Yeah, that's basically everything I have about language ideas. Alright, the idea is that you can also, for example, if we have a format function that formats some value, there's, I don't know, a built-in type of value, which returns type, and then the type info of the type maybe, and that's basically an enum with information about the type. Is this an int, then we do stuff. If we do a struct, then we do other stuff. And this is the case where, tags or symbols or whatever we call them, they can have additional information. So this looks just like, just like a function call down here. So you can basically call a symbol with some values, and then they get attached to that symbol, which allows you to, for example, have something, a variable that is either none or some int, for example. And this is basically like a nullable type. So the type of this would be none or some int. And the type of this would be an int. And the type of, this is just a function. Yeah, don't know how to format that. I think you won't be able to put these type annotations in there. They will always be inferred. Yeah, and some functions, like for example the format function, they don't really have a type. Like, yeah, you can pass in anything, and it will probably return a string or something. Yeah, the struct variant probably has fields in here, and then you can, those fields get joined and, oof, yeah, something like that. Okay. Anyways, let's maybe try thinking about what's the minimal viable example. And I think it's important to, be able to pass numbers and like variables for now. Okay, I think this is a nice first goal of the language. Basically, yeah, just declare things. Ooh, which makes me think, do I want ordering between functions? Like, can I do this? I think inside of functions that would be cursed, but outside of functions, I think it's fine. Yeah. Yeah. So let's maybe have a, like a top level declarative scope without any ordering. You can order things any way you want. So this should work. And yeah, only inside of functions the order of expressions is relevant. Cool. Right. Okay, that's the basic language idea. And I know this is like a very rough, vague idea. Many of the details are not thought out. And that's actually the goal of this video, that I'm just figuring out problems and discovering challenges and working on them as I go along. So I do have a rough plan about how we're gonna implement a compiler, because I already wrote a compiler once. Well, multiple, but that's another story. Yeah, so let me maybe share my iPad screen. Okay. Well, okay. Let's see. Okay, I can draw on this. That's fine. Alright, so we basically want to write a compiler, which means we need to go from, a text file basically with some code in it to something that can be executed. So we know that at some point we have source code. Maybe I'll, this is like a file, just some data. And at some point, I cropped the display, yeah, right there. Okay, at some point we have the CPU in our hardware. and that CPU can execute machine code. So in here we have, a very low-level thing. Machine code is like a pain to write. It's just a bunch of bytes. But the cool thing about these is that the CPU can execute them. And this is not some like magic process or something, but instead the CPU hardware actually understands what these bytes mean. So if there's a certain byte, then it means that some of the some of the wire connections in the chip, there's some current, and then there are some gates, and at the end the instruction does the correct thing. Okay, so we somehow want to go from source code to machine code. That's the idea. And there are some obvious steps we can take. For example, turning source code into, like, for example, some sort of data structure that represents how the source code looks would be a first step. Some kind of tree. And then we probably also want to do, some type checking maybe, and some other things. But at the end, we still want to go to machine code somehow. And doing all of this entire pipeline in one go is difficult, because this is quite a huge gap between this high-level language and the machine code. So I think what we're probably going to do instead is first compile to another language, which is a bit lower level than our source code. So for example, C. Compile to C, like this. And then for C, there's already a compiler that can compile C to machine code, which means we saved ourselves from implementing this part of the pipeline in the beginning, because this allows us to quickly iterate over this first part. And that's important because this is the actual interesting part of the pipeline. This is where our syntax gets parsed, where our semantics, like for example our types and our inference and everything happens. Like the part down here, that's pretty predictable, and that's basically the same among all of the languages. Okay, so then later on, when we have this working and we're kind of satisfied with this part of the pipeline, we can then start and replace that C thing with something custom. And we'll probably first lower to something, not machine code, because machine code is specific to one CPU architecture. Instead, we'll compile to like bytecode, basically a made up machine code that there doesn't really exist a CPU that can execute that, but we can either very naively translate that to machine code, or we can write an interpreter, a VM, which can then run this, and the VM can be written in something that can be compiled to machine code. So basically so in the end we'll probably have something where the CPU can run the VM, and the VM can run bytecode, and our source code can be compiled to bytecode. Okay, yeah, so that's the basic idea. But regardless of what we're going to do down there, the first steps of the pipeline, these right here, they will be pretty obvious and independent of what we do afterwards. So I think we can already start with that and not really worry about what we're going to do later. Okay, so the question is, which language do we use to write this compiler in? And I already mentioned that I created a programming language already, and I think we're going to use that just for fun. So, oh, right, let me share my screen. So we're gonna create a compiler folder, and the language I wrote is called Martinaise. So we're gonna have a Kamin.mar file, perhaps. And in here we're gonna implement the compiler. So you probably don't know Martinaise because like very few people, a handful of people know it. So yeah, this is like a very typically statically typed language. You know, you have structs and enums. They can be generic. You have functions. But I'm basically gonna introduce the syntax and the concepts as we go along. Okay, so the first let's write a minimal Martinaise program. And yeah, programs always have a main function, and it needs to return never, which basically means that the function exits before it returns. And coincidentally, in the standard lib, there's an exit function that takes an it. So this would be like a minimal program. And we also have to import the standard lib, which is that everything is file-based right now. This is not like production ready. So I think I'm going to, I think it's like this. Perhaps. Right, so let's compile this. I'm gonna increase my font size. By the way, Martinaise is architectured the same way. So there's a VM that understands bytecode, and the compiler compiles to that bytecode. The bytecode, by the way, is called soil, and the compiler is written in Martinaise, so the compiler can compile itself. But that also means that you need soil, like the soil interpreter, the VM, to then run the compiler. Yeah, maybe let's first move into the right directory. And now we want to call Martinaise, which is the Martinaise compiler, which you can use to, this is just the bytecode, this soil file, and then you can use that to compile another file to this bytecode, or just to directly run a file. That's what we're gonna do. We're gonna run compiler Kamin.mar. Okay, and it ran. And nothing interesting happened because we just exit. Okay. So maybe let's print something before that. That's a print line function. You can have strings like this, and we see that this outputs hello world. Okay, right. So I mentioned that we have these different stages in the compiler, and I think the best way to go about this, different color, is to first define like the data layout of this, and afterwards define the stage. Like, what do we need to do to get to this data layout? And then define the next data layout or data structure, and define the stage before that. Yeah, so that will be our process. Yeah, cool. Right. This will be an indentation-based language. So I think the first step before doing any parsing, any advanced things, we're just going to convert this file into basically a tree of lines. Yeah. So this will be a tree that has, one empty line, and then one line containing this, then one line containing this, and then some children inside that, namely this line and this line. And same here. So I think that's actually what VS Code is using to display these arrows here. it needs to, convert this file into a tree. Which makes me wonder, what if we do this? Okay, that makes sense. Yeah, okay. So if something is more indented than, the previous line, then it becomes a child of that. And if something is like this is weird, but it's less indented than, it's more indented than this, so it becomes a child of that one. Okay, yeah, that kind of makes sense. Okay, so how are we going to call this stage? It's basically a tree of the lines indented. Oh, I didn't share my screen. Well. So what I discovered is that VS Code basically somehow needs to do that, because you can collapse these indentations. So if you have something weird like this, which is only indented one space, it still becomes a child of this one because it's more indented than that, but not a child of that one. Whereas if it's indented more than this, then it becomes a child of that. So basically we have a list or stack of the open tree nodes with this, and then this is a child. And for each line, we basically check how far indented is it. It's more indented than this, it's more indented than this, so we put it down there. And in here, it's more indented than this, more indented than this. It's not more indented than this, so we are finished with this part of the tree, and we attach this line to this part. Yeah, so we're gonna implement that. And the first thing to do is create a new file, and we call it, so it's a tree of indented lines. I'm gonna call it an indented lines tree, or something like this, ILT maybe. And yeah, I'm not a huge fan of acronyms in general, but for these compiler stages, it really makes sense, because you're gonna be using them all over the place. And if you're gonna read the code, you need to understand the stages either way. But we should document that here. All right, documentation is using pipe characters in Martinaise, which is kind of weird, but well, that's the way it is. So compiler stages, indented lines tree. Yeah, this ILT, and then we'll also import that ILT.mar. Right. Wait, that's kind of weird. Oh, I see. Yeah, empty files are a problem. That's compiler bugs. which actually makes me think, because we are writing the compiler in a language that is not like hugely, production ready or tested. It exists and it does the job, but we'll see how it goes. Okay, so we want to have a tree of lines, which means we have some node. I'm just going to call it ILT, and it has a line, which is a string, and right, string is defined in the standard lib. And so the thing is, in Martinaise, all the definitions and functions and everything from all of the files get put into one namespace anyways. So you can also just import like the main compilation file in here. And if it references some other compiler stages, or if it references anything, that's still fine, because well, all of that gets imported, and this imports the standard lib and so on. Okay, so we have an ILT with a line and children. children are a slice, which is basically a list or something, but it can't grow. It's basically just things of the same type which are placed in memory next to each other. Yeah, and a slice of int. Okay. That will be our first compiler stage. And right. Maybe before converting that, try reading a file. The way that works is that there's a read file function in the Indented. I think we're just gonna hardcode it for now, so why not? And let's just print the content. Yeah. Right, so oops, this read file function returns a result, which is an enum, which has two variants, OK and error. And in this case, reading the file worked. And here are the bytes contained inside that file. So 10, for example, is a new line, and we see that here's a new line, here's a new line, here's a new line. There were 3 new lines, which means the file has, 3 new lines means 4 lines. So this is just the content of the file. So what we want to do is basically unwrap that, which means if it's an error, then crash. This, reading this file has to work. Boom. Now we don't have an OK or something, but only, the bytes themselves. And those we want to convert to a string. Yeah, you convert a byte, you can convert a slice of bytes to a string. Right, so this is the file content. Now we want to convert that content to this indented lines tree. So let's write a function for that. toIlt, which takes content, which is a string, and returns an int. Can this fail? I think it can't fail. Because, for example, VS Code creates these things for arbitrary file contents. We can do that as well. Okay, right. So another Martinaise thing is that it has a uniform calling syntax, which is just a fancy term of saying that if you do this, you have something that looks like a method call, possibly with some arguments. It's basically the same as taking, the left part of this, passing it as an extra argument to a function. And functions can have overloading. So, for example, there's a push function that appends an element to a vector or to a string builder or to something else. And there were just, top-level push functions that take a different type of first argument, and then the correct one gets chosen based on your usage. Yeah, so in this case, we can just do this, and this should give us an int, which brings us back here. And yes, this function claims it returns an int, but it doesn't really. So let's fix that. We want to return an int. Oh, wait. Do we want to return a slice of int, maybe? Because a function doesn't really have like a single root line or something. It's just a bunch of lines, and some of them can have indented parts below them, which become children. Yeah, maybe let's do that. So, I guess parts will be a vector. So vectors are like array lists or vectors in Rust or something, basically growable things. And this will be a vector of ilts. Yeah, and then we will do some things, and then in the end we're gonna return parts to slice, which is the memory of this as a non-growable thing, as a contiguous thing, where you can no longer append anything. So slice slices are like the least common, other the the common interface where you can't append any data. Right, so what do we do in here? We basically want to yeah, for now let's just go over the lines. Yeah, Martinaise has 4 loops. There's a lines function, and we're just gonna push that to the vector. One thing, Martinaise is low level, similar to C or C++. It doesn't look that way, but for example, the push function, it accepts, a push function accepts a reference to a vector. Because if you call something, then basically it's copied by call by value. Yeah. So the vector would get copied if we would have a push function called like this. Which means we need to take the reference of this, which you can do using this syntax. So yeah, here we want to append an int with a line, which is our line, and then children, which is an empty slice of ilts. And for this right here, there's a special syntax, this. Okay, right, so maybe let's compile this. And that doesn't work because we print ilt. Yeah, in here. We print the content to ilt. I don't know why it doesn't show me the error here. That's weird. But basically, oh yeah, we print a slice of ilt, which means we want to print an ilt. But print is not implemented for ilts. We can say print debug, which will print like a default formatting for these. Yeah, and we see that we have the lines of the file. We have a first line, which is empty. We have a line with bar equals foo inside, and we have a line with foo equals 4. Okay, I guess we need to have some sort of indentation in here for this to actually be interesting. And again, I want to indent using 2 spaces. Yeah. I'm not sure if we're gonna enforce that or... Well, anyways, we have these, which is great. Fantastic. Whoa. A lot of lines. Right, so bar is something, and then in here we have 2 spaces and foo. Sure. I guess for the first let's improve the printing of this. So we create a write function that is generic over a writer and writes an ilt. And yeah, the way it does that is by writing with some indentation. So maybe let's say we have a write function which calls writer.write ilt with indentation 0. This. And it basically just calls this function. And writing an ilt with indentation means that we first write spaces, then we write the line, and then we write children with more indentation. And this is like a recursive call. Okay. We probably also want to be able to write a slice of ilts. We're gonna do that. Oops. Oh, come on. We're gonna do that here because this returns a slice of ilts, and we want to be able to just print that. So a slice of ilts can also be printed, which means in here we are just going to write ilts. Let's just iterate over it for each ilt. So for ilt in ilts, do writer.write, and we call this function up here. So write the ilt with the indentation, please. And in here we first write spaces, which means, yeah, let's just do for I in 0 to indentation, which is just a way of saying do this right here, indentation many times. We write double space. Actually, if you just want to call write with a single argument, there's a special syntax for that, which is this writer.that. Okay, yeah. Okay, so we write the spaces. Now we write the line. Yeah, we can also use string interpolation in here. So this will print, the ilt line. And finally, we're going to write the children, which means writer.write ilt.children, which is going to call this with a slice of the children, but with more indentation. So indentation +1. Cool. Let's see how that works. Oops. Oh. Print slice of something. Oh, I see. Yeah, you can already print a slice. That makes sense. So slice already implements write. Of course, in a different way than what we are doing here. So we can't have that, I think. Which is kind of sad. We could have a struct ilts. But just for, just for writing multiple ilts in a more beautiful way, that seems kind of overkill. Anyways, let's do it. Why not? Why not? Okay, you know what? I'm just gonna do content to ilt, and I'm gonna pass an indentation. Oh, right. And do this to standard out. Yeah. So standard out is basically a writer that you can write to. And so this write function calls oops. Okay. All right. So when you call content.toIlt, that basically calls this, which returns a slice of ilt. So then we call write with something and a slice of ilts at an int, which is unique to this function signature. So this function is called, which writes the individual ilts. Right. So let's see how this goes. True, we should put some new lines in here. Ooh. Should we do that here? you know, like before, like this. But then there's a new line at the beginning of the entire thing as well. I don't like that. So instead oh, I hate this. Yeah, I'm just going to create a variable if this is the first thing. Yeah, it's kind of ugly, but you know, if it's the first, then we just set first to false. Otherwise, oops, we write a new line. So this will print a new line before every child except the first one. Yeah, that's exactly what I want. Let me remove the first new line and maybe also, yeah, print else. Okay. New design decision. This just returns an int. But basically there's a root int with a nonsensical line. And it has some children. Yeah. Like this. And then we're gonna print line int and the int. True. Like this. Beautiful. Okay. I mean, look at this. Oh, right. The root int has, oh, okay, this is hacky, but hear me out. Yeah, I think we can just do this, which seems horrible, but I mean, it works. Yeah, write it with indentation -1, and then, okay. Okay, we spend a lot of time on this, so, right, we have a tree of indented lines, which for now is just every line, you know, just printed. Actually, to make that more clear, I'm going to write something before the beginning of each line, like a hashtag maybe. Oh, this is interesting. Well, okay. Oh, wait, how about lines without any children? I think those currently don't exist, but they should work fine too. So for example, if we have this right here, okay, that's fine. Sure. Yeah. Okay, I think what's more beautiful than this is what if we say we print the children with annotation 0. That's the same thing basically. Well, you see it's without the first, the line itself, which is always empty, is not printed, which doesn't really make a difference in the end, but this just feels more clean. Yeah, but as we see, there is no indentation whatsoever. It's just, you know, a row of, yeah, it's not really a tree, it's just a flat list basically. Okay, so let's get to parsing. I guess the first thing would be to have like a stack, or you know, something that contains the ongoing ilts, those that are not finished yet. So I'm gonna have a stack, which is basically just a vec of, there is actually a stack type. I'm gonna choose a vec of ilt, But let's take a different type, like ongoing int, maybe. Yeah. What's an ongoing int? Well, an ongoing int is like an int, but you can it keeps some things like the indentation and basically a vector of children where you can append stuff. You know what, let me figure out how that works on my iPad. Wait, share screen. Okay, and yes, I think that works. I hope that works. So with this drawing guide. So let's see, we have, well, let's say we have a few lines. I'll make it a bit thicker. Like this. Yeah. So let's say we have one line of code that is here, and then there's an indented line, and another indented line, and there's a line here, there's a line here, there's a line here. Okay, how do we deal with that? We basically want to have a stack of open lines, so we just go through this from top to bottom, and we keep a stack, which basically means we encounter the first line and we're like, okay, so we are now parsing this line with this content. Let's keep a list of children that is, you know, where we can append more children, and let's maybe also save the indentation that this line had. And then at the next line, we're like, okay, let's see, this has one indentation at the beginning, which is more than this line, which had 0 indentations. So this is going to be a child of that. So maybe a list of, okay, so the ongoing int only has a list of finished children, which means we have this, this is our stack. And we add the second line with an indentation of 1. And it also doesn't have any children yet, so none. And then we meet the third line, and we basically go through this stack from top to bottom. So the third line has an indentation of 1, which means we check this right here, and it's still a child of that one, because this is indentation 0 and indentation 1 is bigger, but it's not a child of this one. So this right here needs to be finished, and everything below that as well, which means we can then like, okay, we want to remove all the open lines basically that are below this, and we go from the last one to the top, and we basically finalize the children and add this as a child to the previous line. So basically we remove this line right here and add it as a line in here. And then we have an extra, ongoing line. We basically replaced that with this one right here. So then when we pass the next one, we're like, okay, this is indentation 2. Is this a child of 0? Yes, it is. Is this a child of 1? Yes, it is. So we add a new line down here, indentation 2. So then the next line comes ahead with indentation 1, which means we're gonna, go from the beginning. Is this a child of 0? Yes. Is this a child of 1? No. So then from this point on, we have to finalize all of the ongoing ilts from the lower part. We're gonna have to add this as a child to this, and then take this and add this as a child to this. And instead, in our stack of ongoing lines, add this line which we just passed. And in the end, when we reach this line with an indentation of 0, we're like, okay, this is not even a child of the top one. So we're gonna, finish everything. Yeah, add this one as a child to, as a child to that. And add this one as a child to, our global int with the empty line, the root int. Right, so that's the rough plan. I don't know if it got any clearer by me explaining that. And maybe by writing the code, it's better. So an ongoing int is basically a line that we already passed. It has children, which is a vec, not a slice, because we still need to append to this. But those children are finished. They are not ongoing, they are, finished parsing, complete subtrees. Yeah. Oh, and it also has an indentation, which is an int. Beautiful. So then we have a stack of ongoing ilts. And actually our root ilt can be one of those. So let's say our root ilt has indentation, well, -1 basically, because we want every line to be a child of that. So the indentation of every line has to be bigger than that, even those that are indented 0 characters. And yeah, that feels kind of hacky, but that's just the way it is. Yeah, the line is empty, and it has the children are just an empty vec of ilts. Yeah, let's maybe push that or Martinaise. Okay, so we have our initial stack, and then for each line, we just check what's the indentation. Indentation is basically the number of spaces at the beginning of the line. I don't think I have any, way of counting that for now in the language, like in the standard lib. So let's just have a loop. And if the line chars, which is a slice of characters, we get the indentation character, yeah. If that is a space, that's constant, then we want indentation to increase by 1. Yeah, I think that works, right? Else break. Does that work? Okay, let's play through this. We have a line with 1 space at the beginning. So indentation is measured in spaces, I would say, not in like semantic indentation, because you use 2 spaces for indenting. Let's say this is just the number of spaces at the beginning. And okay, so indentation is 0. Which means if the line starts with something that is not a space, if that's not a space, then we break. Okay, yeah. And indentation is 0. That's cool. But if it starts with 1 space, for example, then chars, line chars get 0 is a space. So indentation becomes 1, but then get 1 is not a space, which means we break, and indentation is 1, which is what we want. Great. So a quick note about these control flow things in Martinaise. You already saw that there are for loops, like for variable name in something that can be iterated over do, and then a single expression or multiple expressions with curly braces. And there's a loop which just takes one expression and loops that forever. And these are basically the only two kinds of loops that you have in Martinaise. There's no while loop, for example. You express it using loop. Also, there's a control flow called OR, which is like, if you do this in C, for example, it won't call bar all the time. It will call foo. For example, if foo returns false, then it knows that this entire thing will be false no matter what bar resolves to. So it won't even call bar, even if bar has a print or something inside. This won't get printed. So this is not actually an operator, like plus or minus or something, but it behaves completely different. It changes the control flow of the program. So in Martinaise, there's the OR keyword for that. And I actually come to like using it for, like normal control flow. Because you're kind of saying, well, this is the thing we expect, or what usually happens. And if that is not the case, then please do this. So for example, you can use OR on bools, but also on results or something. So for example, when reading a file, we could also say read file or panic, or print something and return. Couldn't read file instead of saying unwrap. Yeah, but then the toString needs to happen on the entire thing, so you need to parenthesize this. And there are no parentheses in Martinaise, but there are curly braces, because curly braces always, they can be bodies with multiple expressions inside them, but they always evaluate to the last expression. So they are also used for grouping. Right. So you could print this. You could say, well, content is this, or let's make this more beautiful. We're just gonna print this to the error, standard error, or we're gonna exit, and then we're gonna say content is content to string, which basically says let's create a new content, which is the old content converted to a string. And basically after this, you can't access the old content variable anymore, because this kind of shadows it. Okay, so now that you know OR, let's revisit this loop. And so I want to replace this with an OR. Basically, we want to say if this has to be a space, or if it's not, then we break, and then we, just increase the indentation. Okay, so we figured out the indentation. The next part is this right here, going through the stack from top to bottom, or front to back or something, and figuring out which ongoing build are we a child of. So for ongoing in stack, well, we need to figure out if ongoing dot indentation is smaller than our indentation, then we'll just continue. Yeah. Otherwise, we need to combine those ongoing things afterwards into a new node, basically. Yeah. Let me just Okay, so I think having a stack for this is kind of, well, let's try to do this. Maybe we can do better using, you know, if we have a tree, for example, that could be easier. Yeah, let's go with that. Okay, so instead of maintaining a stack explicitly, we basically say we have our int, which is going to be an ongoing int, and it's going to save other ongoing ints, like this. Yes, I know. Right, so then we pass the annotation of a line, and then now we can just walk this ongoing int from the root thing, maybe let's call it root, to some place, you know, as far down in that tree as we possibly can. So the node is first going to be the root node, and again this takes a reference to that so that we can mutate it later on. Yeah, now we basically want to check if the annotation of the node is smaller than our annotation, then this should become a child of that node. Otherwise, yeah, so yeah, this loop basically finds the node in this existing tree that we want to be a part of. So if the node already has children, we want to basically check, are we more indented than the last child? If yes, then we want to traverse down that part of the tree. Okay, so indentation of last child, maybe? Oh, last child. Let's first just save the last child, which is, you know, node.children.last, but a node may not have any children, in which case, you know, there's a last maybe, I think, get last maybe ref or something. No, I think there's a get maybe ref. Okay, yeah. Yeah, okay, so what is get maybe ref? Get maybe ref basically tells you, well, this is weird. Yeah, that's, you know, I created a standard library for my language, and it's kind of wonky or like untested in some places. So let's see the vector. It has a get, yeah, it has a get function where you pass an index and you get, you know, a copy by value. Yeah, basically a copy of what's inside the vector. there's a getRef, which returns you a reference to that thing in the vector. So this is actually a pointer to, you know, the place in the vector where the thing is stored. Which means if you override that, then it also gets changed in the vector. There's also getMaybe, which returns a maybe of something, and there's getMaybeRef. There's also, for convenience, you know, a last, I think, and a last maybe, apparently, or just a last maybe. You see that it's really inconsistent how this, like, you know, whether functions exist or not. And by the way, these vec kind of like constructors is like these ugly, no, it's just a function that creates a new vec for you. Yeah, this is definitely ugly, but at least the ugliness is contained to, you know, the vector in the standard library. Okay, so I think we're just gonna go use getMaybeRef, which should accept this right here. That's why I was wondering. It should accept a mutable vector. Same as this, by the way. Yeah. So getMaybeRef of the last thing, which is node.children.len -1. And this call doesn't work because getMaybeRef is called, needs to be called on that. Okay, so now we have a last child, which is a maybe. So it may exist or not. Yeah, so this is maybe. So we need to handle the case when it doesn't exist. If there is no child, then we want to append ourselves to the node directly. So we break out of the loop. But if that child exists, then if, you know, last child dot indentation, if the child is more indented or equally indented as ourselves, then we want to break. Because then we don't want to be, you know, a child to that thing, but instead we also want to be appended to the node directly. But otherwise, if we want to get appended to that child, then the node basically becomes the last child. Okay. And then we append ourselves to the node. So yeah, basically this node.children.push ongoing ild with an indentation, a line, and children, which is a vec of ongoing ilds. Yep. Okay, beautiful, I think. Yeah, and here we need to convert that root, you know, to from an ongoing ild to a normal ild. Right. Yeah, maybe I'll quickly draw how that works. Oh, sharing screen. Hang on. But this is, I think this is more elegant than the approach I had in mind before. Okay. So yeah, rather than you know, doing all of that, we're just creating a tree as we go along. We are creating a tree. Let's maybe name the lines A, B, C, D, E, F. Yeah, we have our tree of, you know, the root tree, the root node, which doesn't really, you know, exist in the file. And then we're like, okay, let's try to, we are at the A node. It has an indentation of 0. So the root node has an indentation of -1, which means, yes, we want to be a part of that. It doesn't have any children, so, you know, we would break out of the loop and we would say, let's append ourselves to that. And we say, well, our indentation, by the way, was 0. And then we're at the B node, which says, well, I have an indentation of 1, so I'm gonna, hang on, yeah. So I'm gonna be part of the root node, which has an indentation of -1, mine is bigger, so I want to be a child of that. Look at that, it actually has children already. There's a child A, that's the last child of the root node, the last and only child. And it has an indentation of 0, so I want to be a child of that. So then I'm gonna append myself down here with an indentation of 1. And then C comes along, it basically goes here, oh no, that's too big. Let's stay here, and it gets appended here. And then D comes along, and it starts at the root node, and goes here, and then it only looks at the last child, which is C. And it sees, well, my indentation is bigger than C, so I'm gonna append myself to that with indentation 2. And E is gonna go the same path. Well, this is indentation 0. Indentation 1, no, that's too big. Let's not go down there. Instead, let's append myself here. And for the F node, indentation, it starts here, goes here. Indentation 0 is already too big, so it just appends itself to the root node. Okay. And look at that, we have a tree representing the indentation of the file. Oh, well, I see. There's myself in the, kind of blocking the view. Maybe this is better. Right. Okay, so that's basically what's happening here. We start at the root node, and we want to figure out what node do I want to be a child of. So if the root node doesn't have any children, we're done. We just, we want to be a child of that. Otherwise, we look at the last child, and if the indentation of that is bigger or equal than our own, then we don't want to be a child of that, so we also break, and otherwise we traverse down that child. Okay, so converting ongoing ilts to ilts. Yeah, let's maybe create here to ilt of an ongoing ilt, which we're also gonna call ilt because why not? And yeah, it's an ilt with a line of the ilt line. The indentation we don't need to save, and the children are the ilt children converted to a slice, so you can't append any more data to that. Slice ongoing. Oh right, yeah. Yeah. So that's the weird, or maybe underdeveloped part of Martinaise, is that it doesn't have higher order functions like map or filter or something. So we're gonna have to create children, which is a vec of ilts, and then for each child in ilt children, we're gonna have to do children.push child to ilt, call ourselves recursively, so that we can do children.toSlice down here. Okay, so this should hopefully work. Let's see. Is there any... Where's my terminal? Down here. Well, that's bad. Okay, what happened? We call to ilt on a string, which calls get. Oh, right. So up here, yeah, where we find out the indentation. What if a line doesn't, like if a line is empty or it only contains spaces? We basically want to skip that line, right? Because assume we have, a long body and it's like this. I think this should still be like part of the bar thing. Yeah. So let's just skip empty lines right here. So if line.trim.is empty, we continue to the next line. Beautiful, maybe? Interesting. Wait, let's look at this. So we have a bar, which contains a foo. I'm fine with that. But it should also contain the bar, right? This bar just gets omitted entirely. And then there's the bass and the for and the foo. I'm fine with that. This is, I should add a new line after the line itself. Yeah, true. Yeah, that's more like it. But still, where's the bar? Wait. Now it also doesn't look right. We have the, okay, maybe let's first fix the formatting and then look at the bug. So this is a line with an indented line below. Okay, so we have the children. Oh yeah, this should only be done if there are any children. So if build children is not empty, then we also write a new line. Yeah, look at that. Okay, now let's look at the bug that the inner foo, the inner bar doesn't appear. I'm actually gonna zoom in a bit more because why not? I can also do this. Look at all the saved space. Where? I guess let's just print the lines. Like print debugging is always fun. We have a line. Bar, foo, wait. Oh no, I didn't save this file. But sometimes, okay, yeah, so this gets passed correctly. We have a bar equals, and then a foo, and a bar, and a bass, and a for, and a foo, and a for. Okay, and this is really error resilient. So for example, if we do this, or we have, a weird amount of indentation, this still gets passed correctly. Oh, I'm realizing the lines still have spaces at the beginning. We should probably fix that. So, we figured out the indentation, and line is line.trim, which trims white space at the beginning and end of the line. Okay, this looks clean and quite robust. Like normally indentation-based languages are very particular about, you have to put this many spaces here and there, and I am gonna have a sane default, and maybe someday I'll get around to writing formatter. Then I'll also choose a reasonable default, indentation, like enforce 2 spaces, for example. But it's nice that it's resilient and predictable. And I think we are done with our first compiler stage. So we converted our file to something, basically a tree that looks a lot more like the file structure. Next compiler stage. Let's let's convert it into a tree. It is already a tree, I know, but more like a tree of syntax items. I'm gonna call it abstract syntax tree just because that's the the industry standard name for this kind of thing. Yeah, I should also probably say this is an indented lines tree, int. I mean, that's obvious. A tree that contains all the lines of the file structured by their indentation. Yeah. Oh, nice. In Martinaise you can put 2 spaces at the end of a comment line to basically have a title. And this is like formatted as a title. And yeah, at some point I had my own my own editor, which also, like, you had a shortcut that basically only showed the title comments. So if you have a long file with multiple, multiple sections, basically, you could quickly jump to a section. I should drink more. Like, I already realized that my voice is getting rough from talking so long. It almost seems like streaming is an actual, something that requires effort. Crazy. Okay. We have our indented lines tree. Next, the abstract syntax tree. You know what? I'm even gonna put that up here, like a description of the module or something. So the abstract syntax tree is a tree that represents the language constructs kind of wishy-washy, to be honest. Well, well, I think it's fine. Okay, so what is an abstract syntax tree? Yeah, in here we saw that the _lt is a struct because all of the _lt nodes were basically the same. In the abstract syntax tree, it's probably going to be an enum because these are going to be like the language features, basically. We'll have, for now, very minimal features, like probably a definition, right? Import this, a definition. Which stores inside a definition. And yeah, Martinaise doesn't have namespaces, so we use prefix everywhere with a name for now and a value, which again is a must. Cool. Yeah. Or it can be an int or a name. Like a reference to a variable or something. Let's start with that. I think that's already like plenty to implement. And let's maybe write a reasonable example file. I wanted to say program, but calling this program is a bit optimistic, I think. Okay, so we have a reference. We have this would be a name. This would be an int. This is a definition of who. Containing this. Yeah, I think that's already enough. Cool. Let's try to pass this So parse. We're gonna get an int, right? Yeah. We'll get an int, and we want to produce an ast. Cool. So basically, let's think through this. Oh, for now we could even just be like, hey, if this entire thing, so you know, if int.line, if that's a number basically, I think there's parse digits in the standard lib, I'm not sure. Or parse int or something. Oh, I see. So that's a weird thing about Martinaise, that it only gets that functions only get analyzed when they're used. So ast is int to ast, and we need to import ast, and maybe add this. Cool. Right, so doesn't show any errors, which is weird. Let's just do that. Okay. So the analyzer is not stuck somewhere. No definitions named to ast. Int to ast. Importing this. Alright, it's called parse. Let's call it to ast. Oh, look at that. We have errors. Cool. So, okay, parse int exists and returns a maybe int. Yeah, basically if this returns sum, then we want to return it. And there's syntax for that. If this, and then notice if is a language construct. So if this is sum int, then, and here we have int as a value, as a variable. And that's basically equivalent to doing this. You know, we switch on that. Switch doesn't need braces here, so there are two cases, sum and none. In none we do nothing, in sum we take the int payload that this enum contains, and we do stuff. The if is basically a shorter way to write this into this. So what we want to do is we want to return an ast.int with the int. Yeah. Otherwise, we want to return ast.name of the line, because why not? Yeah, and maybe let's print the ast, which will probably be similar to printing an int. I'm not sure. I think we will have indentation, maybe. Let's see. So we want to print an ast, which means printing an ast basically means we want to print the ast with an indentation. And here we want to switch on what kind of ast it is. If it's a definition, then we want to print def maybe, and then the definition name equals, yeah, for now that. And if it's an int, we want to just print the int. Similar for name. Okay, yeah, I like that. Maybe let's reorder them from like very simple, fundamental things to more complex, complex constructs. Of course, this parsing is not valid. You know, this like a definition never gets created for now. But let's see what it does. It never prints the ast. Well, that's unfortunate. Oops. Ast should be the ast that we just parsed. Okay, ast is 0. Oh, I see. Yeah, so the thing is, there's an ilt with the root, you know, the root ilt with an empty line, which contains all the other lines as children. Currently, we are just ignoring children in here. So we just have the root line, which is empty. And apparently parseInt also works for empty strings, parsing them into 0. Which is weird behavior, I think, but okay. Okay. What can we do? I think a nice plan would be to maybe go over the children first. No. Parse the line. Or, yeah, I think I'm gonna have a different function for turning ilts into asts. Yeah, and that's gonna go over all of the ilts. So wait, it creates asts. Right, and this is that. And for each ilt in ilts, it's gonna append ilt dot to ast to the asts. In the end, it's gonna return the asts. Yeah, kind of like this. And then for now in here, let's just say ilt dot children to ast. Okay, so the ast is this. I don't quite know what to make of this. Why is it? Oh, yeah, because it's a slice. In fact, I think you can. We want this to be a tree, but every part of the tree I think you can just, you know, have multiple things in here as well. You could write this. Yeah, okay. Maybe. Let's change this up here. Let's say this is an ast expression. And then we have an ast which has a number of expressions inside. Oh no, like ast, I don't know, body, yeah. Children or explorers, children being a slice of ast. I'm gonna call it, yeah, like this. Okay, so the file gets passed into an ast body. Yeah, an ast body. And yeah, so we need to create an ast body with expressions, which is gonna be this, and an int gets converted into an ast expression, which is either ast expression name or int. Yeah, you can write an ast expression for sure, but if you write an ast body, then it prints, oops, ast body, then it prints the, you know, for expression in ast. And body explorers do writer dot write the expression with annotation 0 for now, you know. Okay, ast def refers to ast, but that doesn't exist. True, because that has to be an ast expression. Okay, yeah. I kind of like that you don't have these generic names like ast for variables, that, but you know, this is an expression. An expression is like anything that results in a value, like bar is an expression, 5 is an expression, foo is an expression. This assignment here, this definition is an expression. So yeah, this does work, okay. Why does that work? Because, oh yeah, because we print these things right here, but we want to print them with new lines coming after them, like that. Okay, we have a foo, we have a for, we have a foo, we have, yeah, this is just a name for now. Right. So a problem is that, you know, if we organize everything into this neat little tree, I think it might work. Let's say we call a function with 1 and 2. Let's say add 1 and 2. You know, just do this. Here we define add of a and b as, you know, adding numbers always results in 5. We want to be able to parse this. And currently these are just, this is a name and this is a name. That doesn't make any sense. So if we have a line, it can be really complicated. Like the thing that can be in a single line of code or in a single, you know, node in the tree, you could probably have some floop and then, like, you know, we'll probably have, yeah, I don't know. You could have something like this in here, and take that times 4, something like this. Even look kind of, you know, Lisp-like in the syntax. You should be able to do that. So the lines themselves can be pretty complicated, which is why I think it makes sense that we add a parser for those, just for a single line. So creating parser, creating a new struct, parser, which is basically gonna, you know, walk through the entire line from beginning to end and it's going to try to understand what's written in the line. The way that's going to work is it has the input line, it has the cursor, and well, that's basically it, I think. And then there are a bunch of functions that take a parser as the first argument. So one would be to parse an int. So we don't need to do this right here. Instead, when we have an int, we are just gonna create a parser, you know, with the int line as the line and the cursor starting at 0. And then we have parse int, which either works or doesn't. So maybe. Yeah, this is not called a line, this is called input. Beautiful. And then in here you could do parser dot parse int, which is going to call this, which does things. And I think I'm just going to look at how parse int is implemented in the standard library. So let's open that. Martinaise, standard lib, and I think int or string. Don't look at this. Well, you know, you can write functions in basically assembly, or like bytecode that gets turned into assembly, or rather machine code, and all of the built-in functions, like an int for example, is just a type that is 8 bytes big, and all of the operations on ints, they are actually defined in the standard library like this. And the way that works is if you name a function, you know, you can either name a function something like this, like only letters and underscore, or you can name it a combination of, there are some symbols like plus, minus, times, you know, star, slash, I think backslash, and dot, and whatever. So all of these functions, like you know, this right here, a dot dot, is just a function that takes an int and another int, and it returns a range, and then you can iterate over the range and so on. So you can write your own operators in Martinaise. And this plus actually calls this, sorry, this plus function right here. Okay, but we were looking for the parse int. Parse int down here. Okay, it's kind of similar. Well, no, it has a number, which is the number that we pass, and for each character we check if it's between 0 and 9, so if it's a digit, then everything's fine, otherwise we return, hey, this couldn't be passed, this number. And then we take this number, we set this to the existing one times 10, so basically shift this one digit to the left to make space for the decimal, you know, like the the new digit, which is between 0 and 9, and then add that digit. Okay, yeah, we're probably gonna do something very, very similar in our AST. We want to parse an int. So we have a number, and we have cursor start, and basically we check, hey, parser okay, we loop. That's the first thing. We loop. So we want to get the current char of the parser, and we do that by saying, hey, we want to have the input, the characters of that, and we want to get what's at the cursor. Get maybe, because maybe this, you know, we've reached the end of the string. In that case, we want to break. And now that we have the char, we basically want to check if it's, that it's in this range of characters. If it's not, we want to break. And then we basically do this. But we don't want to return 0 if we couldn't pass any number. So we're also gonna save the start cursor. And if start, you know, if the cursor didn't advance, then we're gonna return empty, or like none. And we also need to advance the cursor down here. Yeah, I'm gonna create some helper methods for that really soon. Okay, so we can pass an int. And yeah, in a single line there can be something really like complex. So what we really want to do is just pass an expression. Returning an asked expression. And you know, if it's an int, that's fine. We can say if parser.pass int you know, is some int, then we want to return that int. Beautiful. And similarly, we're going to do if parser is, you know, we can pass a name, then we want to return that. And we also need to wrap those. And if none of those could be passed, then we return none. Right, so parse name doesn't exist. And we should probably implement that, parse name. Basically parsing, you know, like a lowercase name. Okay. Right. So then when we convert an int to an expression, what we really do is we create a parser and we pass an expression. And that should work. If it doesn't work for now, we're just gonna panic. Expected expression. And yeah, we're gonna return that. I don't know, to do stuff with the children, because this is just parsing. You know, if we have this, then this is basically gonna tell us, well, I passed an expression, maybe like a definition without a value or something, or it's gonna pass everything up to this point. And then if we see, well, the next one is an equal sign, that's the only thing that's left, then we pass the children as well. And otherwise, if there was, you know, if there was something like this, then this shouldn't have any children. And if we have something that's, for example, a name, you know, this gets passed to a name, then having indented lines below should actually call it, similar to this. Ooh, if you have this, then this is basically a call which evaluates, you know, this is like, it doesn't work with add, but I think this should probably be a call. Yeah, a call that gets executed first, and then the result of that has to be a function that is then called with these arguments. Maybe. I think that makes sense. Anyways, depending on the expression that we get from this, we need to integrate the children differently. If this is, anything, if this is something like this, then it's a definition, and those are just like, passed into like ast body or something. If it's this, then they become call arguments. If someday we'll probably have structs or something that are also going to need syntax, where all of these are probably struct fields, or when we do a switch. Yeah, but we'll look at that later on. Right. Yeah, parsing is what we wanted to do. So similar to this, we're just gonna save the start and loop and return at the end. But we don't actually need to like aggregate a number. Instead, we'll just check what's the character, and this should be something like this. Actually, I think there is, in the standard library, there are functions for this. There's char dot is digit, and there is char dot is letter. Yeah, and it should either be a letter or it should be, an underscore. Oh, by the way, didn't mention that. Characters in Martinaise can be written with hashtag. So you write a hashtag, and then whatever comes after that is, this whole thing is a character. So this right here is the way to write an underscore character. Yeah, we don't need this. We advance the cursor. The end is the parser cursor now. Yeah, if the start and end are the same, we couldn't parse anything, like there weren't any letters or underscores or whatever. Yeah, this is gonna return string. But if we could parse that, then we want to return the string that goes from start to end. So parser.input.substring from start to end. Beautiful. Beautiful. Okay, let's maybe try to run this. It actually works. Crazy. Oh yeah, it's just an add, and then the parser stops. And we're done. I mean, sure, that works. Yeah, we need, more complicated things. We need to pass calls. So let's add a call in here. Call is an ast call. What's an ast call? Well, an ast call has the thing that is called, which is typically called the receiver in programming languages, and it has arguments, which is going to be a slice of ast expressions. Oh, by the way, these ampersands are here because, as I said, Martinaise is a low-level language, so you can't have recursive types. So ast expression can't contain, if it contains an ast call that returns that contains an ast expression, the size of this will be infinite. So this needs to be a reference or like a pointer, Yeah, I don't handle ast call in here, so if it's a call, then we're gonna have to write call. Actually, I'm gonna, this is more like a debug print, I think, but call.receiver and call.args. Yeah, just debug those, I think. Cool. For now. We'll change this later on. Okay, so we have names right now, which is fine. And we actually need, we need to pass something like calls. And to do that, I'm gonna rename this to parse atom. We're just gonna be like parsing something, you know, that doesn't contain a space. Something in a single int, a single name, but a call is something more complex. And a call is basically just space separated atoms. Yeah, so an expression can be just, we're like, hey, parser.parse atom. We do that. Or if that doesn't work, then we return none. And then we're gonna say, you know, if there was additional stuff in the line, if the parser is not yet at the end, then we may want to parse all of those other expressions and turn them into arguments to the call, basically. Okay, so how are we gonna do that? You know what? Let me make a quick break and get something more to drink. And actually, I'm gonna okay. Yeah, I'm back. I had some lunch. I have fresh iced tea. I really should drink more. Okay. Yeah, where were we? We had expression parsing, right? So instant names are atoms, and now we want to parse other stuff. For example, calls. And to do that, we parse an atom, and then we basically want to pass arguments. We're just gonna be a vector of expressions, and you know, then we're gonna pass them. And in the end, we can check if we couldn't pass any. So if args, you know, is empty, then we're gonna return just the expression. Otherwise, I can also just do it like this. Otherwise, we're gonna return, we can also do it like this. Beautiful. As we're gonna return an ast expression dot call with an ast call, where the receiver is the expression and the args are the args. Yeah, this doesn't work because it expects a slice, of course. Yeah, maybe. Actually, you know what? Controversial opinion. I like formatting ifs like this because then you have the, you know, the then and the else thing make very parallel structures. And it's actually more compact than, you know, having then here and an extra line in between those for the else. Right, but anyways. Args to slice. And now it complains because the receiver has to be, alright, a pointer to an ast expression. And the way to do pointers in Martinaise is there's a function put on heap that basically takes a value and allocates memory for that on the heap, and then returns you a pointer to that value. And I'm just realizing I haven't shared my screen yet. Okay. Well, this is what I just wrote. So yeah, we basically pass an atom as the receiver, and then we try to pass arguments, which we still need to do here. And if we couldn't pass any arguments, then this is just a single expression. Otherwise, this is a call where the receiver is the expression which we put on the heap, and the arguments are the arguments that we passed. Yeah, and this put on heap, it basically just puts it on, we can even go to the definition of that. It puts it on somewhere in memory. So memory in Martinaise is kind of weird. Because usually you have stuff like, you know, it performs a syscall or something to allocate memory. But Martinaise was designed with more of an, there was these things called fantasy consoles or fantasy chips or something. And this was designed just like one of those. Just to give you an idea, let's maybe, yeah, show that Pico 8 is the most, yeah, Pico 8 Fant console. It's basically like a, you know, it's like a bytecode or like a specification for a console, and then people can write games for that. And it's like, you know, you have this amount of memory, you have these instructions and these syscalls available, and Martinaise does something very, very similar. So the bytecode that it compiles to is soil, and there you just have a big memory region that you can use however you wish. Which means that you have to care about allocations and so on yourself. So the way it works is the put on heap function creates an uninitialized t and then initializes that and returns the reference. And the uninitialized t basically calls malloc with a size of the thing and the alignment and turns it into a typed reference. So malloc just returns an address. This turns an address to a reference. But this memory is never really freed in any way because, well, you could save some metadata in there and then have some sort of, well, let's trace all memory, but didn't need to do that. And this approach is way simpler. And if you really think about it, a compiler is just something, you know, you run it once, it allocates some stuff, and then it publishes or results in some bytecode. But then you can just free everything at once, and maybe even let the OS free everything. You don't need to like go ahead and be like, okay, we created bytecode which we wrote to a file, so now let's like carefully traverse all the trees and stuff that we created and free all of those individually. That's like, why do you do that instead of just letting the OS take care of that? Yeah, there is some kind of, like, you can say, let's basically take a snapshot of the heap right now, or basically save what amount of the heap is used and what isn't used. And then you're like, okay, now I want to free everything allocated after one of those snapshots or checkpoints. Because the way that malloc works is it basically just bumps allocate memory. So it has, so if you allocate something, it puts it right in memory. And if you allocate something else, it puts it right next to that. So it basically just maintains a single pointer, this heap head, and it moves it forward as you allocate more memory. And that's it. And when you take a checkpoint or snapshot, checkpoint, it just saves where the pointer is. And then when you allocate more memory, you can restore it to that position. But that's all of memory management in Martinaise. Very simple, very crude. for long-running programs like servers or something, this is like totally ill-fitted. But for simple stuff, what Martinaise is intended for, or at least initially was intended for, like run a program which runs, I don't know, a few seconds maybe, and then prints stuff or does stuff, and then it returns. For those kinds of programs, this approach is totally fine. So I did some advent of code stuff in there and the compiler itself, and for those use cases, this approach is perfect. Right, so here we just allocate memory on the heap and save the expression in there. By the way, that's also what slices and vectors internally do. So that's why those don't, we already leaked memory on the heap until now. It's just that this is more explicit, kind of. Okay, but on to parsing expressions. So we finished parsing an atom. Now we basically want to say, we have a loop, right? And we say parse another atom. If that doesn't work, then we're done. We break the loop. And the resulting atom we push to the arguments. Yeah, that's basically it. Easy. I can zoom in a bit more actually. No, I can't. Well, that's unfortunate. And to be honest, I'm not really using this side thing, but I don't know how to deactivate it. I can just switch in and out of send mode. Maybe. Right, so we have this. Let's maybe, close some of these. Let's close all others. Why not? Okay, we can parse expressions. Next step would be to actually use that. Or do we do that? Yeah, we already do that. Let's try it out. Oh, look at that. That doesn't work. So we have a name. Oh, and then there's a space. And we say parse atom with a space at the beginning, and parse int is like, whoa, space. No, that's not an integer. Name is like, well, that's not a letter. So that's it. I think we should parse white space in between those. So maybe I'll add another function. Not really parse, but consume white space, because we don't, this returns nothing. We don't do anything with the result. And it's basically, well, we basically do something like this. So we say, hey, parser input chars get maybe parser cursor, or just the current character. And if this is white space, then we move the cursor, one to the front. And then we're done. Okay, so in parse, we can even do that at the beginning of parse atom, right? Consume white space, like this. Oh, look at that. Wait, let's have a look at our file, which was called test. Wow, we have a call of name with the arguments 1 and 2. Indeed we do. And then we have a name add. Well, yeah, that's this line, and the children get ignored. So we need to fix that. But then we call add with A and B. Yeah, and the equal sign, ignore that. Nice. That's really nice. So we passed an expression. Now there's to do stuff with the children. Yeah, basically, I think we need to think about how would we do that. Yeah, I think we would just pass the children separately, like, you know, children is int.children, which is a slice of ilts. Convert that to an ast, which gives us an ast body. Oh, okay, yeah, sure. And then we basically switch on the expression. Yeah, and we need to handle all cases. So if it's an int, yeah, it doesn't matter what int it is. We don't want to be able to, you know, call an int or have some children below that. You know, writing something like this is definitely wrong. But we could allow that, actually. We could just say, oh yeah. Yeah, we can just say, if the children, you know, the expressions are not empty, then the expression is a call. It becomes a call of an ast call, where the receiver is the original expression and the args are the children expros to slice. It already is a slice. Yeah, but something like this. Okay, I like that. Oh wow. Okay, let's look at that in more detail. So we have a call of add with 1 and 2, beautiful. Then another call of add with 1 and 2, because they are indented. That's beautiful. And then we have a call of add A and B. Oh yeah. And this call results in something which is then again called with 5. Yeah, we somehow need to like pass the equal sign at the end. And it should probably be an error if the parser couldn't pass the entire line. But okay, here 1 is called with fundbar, which, you know, doesn't make any sense, but we can pass that, and some future compiler stage will figure out that this is nonsense. Okay, that's cool. Yeah, let's maybe. Oh, there are so many things we could do. I think let's first look at printing these, because that's something that makes all the other development much easier if the printing is good. Yeah, here we already have an indentation, and basically we want to be able to do the same with an ast body. So, you know, being able to print an ast body with an indentation would basically just mean that that the the individual expressions, they get printed with an indentation of indentation. Okay, yeah, that makes sense. And write would just call writer.write body with indentation 0. And then in here we have an int, a name, a call, and a call I think should, you know, have the receiver right here and print that directly with annotation of course. So writer.call and then write call.receiver with indentation, and then writer dot for arg in call args do writer dot that's just writer dot write. Oh, okay. Well, that's kind of weird, but let's do it like this. Okay, this doesn't work because ast expression and int. Alright, the receiver is a pointer, so we need to dereference that for the function overloading to work. And def is just weird for now, but it's also never created, so maybe we don't need defs for now. Oh, well, this is, yeah, for the name, let's just omit that. And similarly for the int, actually. Maybe even here. Okay, yeah. Okay, yeah, I need indentation. I need to somehow write indentation. So let's just say for I insert to indentation to writer dot print 2 spaces, please. Okay, so this is like a very rigid structure of the ast. We say we add 1 and 2, we add this. Oh, this is interesting because we add 1 and A and B and then we call that with 5. Ooh, that's weirdly formatted. Very weirdly formatted. I don't like that. Let's maybe for calls, you know, do it like that. Yeah. Yeah, that's a tree. So we call add with 1 and 2, we call add with 1 and 2, we call the result of calling add with 1 and 2 with 5. And in here we also only printing this, you know, the first thing like we had in the other, in the ilt. If it's the first, then first is false as writer print a new line, please. Okay, so we have a tree that represents what we're doing. We call some things. Now let's look at this. Oh. Okay. Parsing a definition. How do definitions, what do definitions look like? You know, I just wrote this down here. We could also say that we have, like, you know, this like in rock. We have like a special fun keyword. or even here at the beginning. Or we have other stuff. Well. Okay, I think in the parser we can. I think we're gonna go with this, what I initially had in mind. This. And we can fix this in the parser. So parse expression parses first a single expression, then arguments. But then what if we check, like, you know, we say parser dot consume white space, and then if parser dot input dot get maybe parser cursor, or, you know, something else, if that is an equal sign, then this is a definition. With a call, so the expression right here needs to be a name, basically. Let's see, in here, name is, what is this? Like, right. Okay, so let's maybe not do this. Let's do something like this instead. If the args are not empty, then the expression becomes a call. Wonderful. So we just integrate them in here. And if the next character is a, you know, an equal sign, then parser dot cursor equals parser dot cursor plus 1, and we have a definition where the name is stuff. With a name. Maybe let's basically in this case, for example, if we say like this, that's invalid. The question is that already invalid in the parser, or is it that handled by a later compilation stage? I'm just realizing my camera doesn't work anymore. But now it does. Yeah, cool. So we don't want to allow this, which means let's maybe we need to ensure that the existing expression that we have is either a name, in which case we just define a variable, or it's a function definition. Yeah. can just say this is a name. Yeah, like that. Okay, so basically we want to switch. We want to switch on the existing expression that we have. If it's a name, then it's just, you know, something like foo equals 5. And in that case, we want to say that the definition is just that. The value is, oh, whatever comes after this. Yeah, probably parser.parse expression, a recursive call to ourselves. Yeah. Okay, if it's something else, you know, like a call, for example, then we are like, oh, this is like something like foo ab equals other stuff. In which case we want to check. In which case we need to make sure that the thing that's being called is a name and not, you know, like another call or number or something. So in this case, we basically need to switch on the expression again. We can rather say name is, you know, call dot receiver dot name. And by the way, receiver is an ast expression, which is an enum. And if you call dot enum field name on an enum, this returns a maybe. That is either some, if the enum is actually of that, you know, if it's a name. Yeah, if it's a name, then it returns some string. Otherwise, it returns none. So we can just do that. Or panic definition of something weird. Yeah, and then we just return this. Well, we update the expression with this. Right, ast definition. Yeah, and the value. Now the value is interesting, because in this case we're actually defining a function. Do we want a special node for that, special ast thing? Not is empty. No, is not empty. Oops. I don't think so. I mean, you know, we could have ast def and ast function def, basically. But I think what's more elegant is if we have like a fun value, basically. And functions just turn into a definition where the value is a function. Yeah, so let's have an ast fun, which takes parameters, which is a slice of strings. Right, we need to ensure that. And it has a body. Right, so Yeah, by the way, the difference between arguments and parameters is usually that both mean the same thing, but parameters is from the point of view of something like of the function body, you know. You have these parameters that are like variables you can use. And from the point of view of calling a function, those things you pass in are arguments. So when you call a function, basically you provide arguments and they become the parameters of the body inside. Subtle distinction, but right. Okay, so never mind all that. We have a function which takes parameters, has a body, beautiful. Okay, the default case. What's the default case? The default is just panic. Definition, weird definition. Right, and the value is a maybe asked expression. Right. Definition without value. Try to send asked expression of the field of that type. Right, so this entire thing needs to be put on the heap. Well, not beautiful. We're definitely gonna refactor this. Yeah, ooh, something similar goes down here. And right, but this, no, not like this. Instead, the ast, this results in a function, which is an ast function with parameters, which are gonna be here. Params are, you know, just strings. And then for each arg in call.args do params.push arg, which is an ast expression, which has to be a name, or panic of fun with non-name arg, I don't know. Right, and the function has params and body, and the body is basically an ast body, I think. Yeah, an ast body with expressions, which is a vec containing the expression converted to a slice. I mean, that's wow. Wow, just wow. Expected a closing brace. Where? This works out, this works out. Oh, yeah, like this. And this, what? Something weird is going on here. No. We have this, and then that. And then that, hang on. No. Oh, I see. Like this. Yeah, we have the ast body, then we have this with that. Okay. Yeah. Okay. Yeah, this entire ast expression needs to be put on the heap. Okay, now this works out. True, we can't print those. Yeah. Oh, by the way, fun is a keyword, so I'm using a trailing underscore to make sure it, you know, gets highlighted correctly and so on. Okay, so if this is a function, we just treat this like the call, basically. Like the call. Except we're writing it on fun. And then on the same line, yeah, on the same line we can write the parameters. You know. fun parents. And then we print a new line, and then we print the function body, which is the fun body. Okay. Wow. Definition without value. Well, oh, that's actually true, right? This right here. Yeah. Let's change it. Boom. Okay. Weird definition. Weird definition. Okay, so there is a definition of something that is not true. This is a weird definition. Okay. Wow. We have an ust, which has, you know, some calls. What's going on here? That's certainly weird. That is super weird. Hang on. A call. I don't get it. Mm-hmm. What? Like this, I expected. You know, we have a definition of add, which is a function that takes an a and a b, and it has a body that is just a 5. But then it goes on to say this is wrapped in a call to a and b. Oh, oh, I see. So we have this down here. We changed this to, you know, just update the expression. But then down here we still wrap it in another call. So this should just be that. Yeah. Okay, yeah, we call add with 1 and 2, with 1 and 2, and then we define add as a function with parameters a and b and this. And the define looks ugly, so let's change that. Yeah, the name equals, and then I think we should print the value on a new line. Oh. No, not like this, because the value is probably a reference, so we need this. Okay, yeah. Oh, look at that. We define add as a function that takes a and b and returns 5. Beautiful. Beautiful. Now we want to support, you know, like multi-line functions, stuff like this. And this doesn't work because this, oh, this is a definition without a value. That's horrible. So maybe let's not do that, and instead, you know, where we have parse definition, parse expression. Yeah, this directly updates the cursor, which we don't want. Parse equals. Yeah, then we check that the left side is something, and then we pass the rest. We can first of all factor this out, so we can say a value is parser.parse expression, or or panic for now, and then this right here is just the value put on the heap. Similarly for a call, we can just say, well, this is that. It's a function with an asked body with a single value inside. Beautiful. You know, I really like formatting code to be compact, because I like how you can then more quickly scan the code. You know, sure, it's a bit more, you know, a bit more dense and a bit more I don't know, it is more dense, but you can orient yourself. You know, the keywords are highlighted, so you switch, and then you have all of the cases right here, and it's pretty, I like dense code in general. Right, so we have this, and basically we want to allow a trailing thingy. But if there's no value coming after that, then we're just gonna stop parsing. So basically, if you know this is that, then well, if that's the case, then we want to check if we can parse an expression. Because only then we want to do, you know, this entire thing. Yeah, I'm gonna do it like this. Technically would have to be one more level of indentation, but meh. Yeah, so rather than doing this, we only advance the cursor and thereby consume the equal sign if there's a value coming after that. If there's not, then that's fine too. You know, then we just parse a call. Let's see, here we have call of add A and B. Yeah, and then this doesn't happen in, you know, parse expression, which only works in a single line, but we basically have to do the thing in here, where we say if the, you know, if the children are not empty, then we're going to wrap it in a call, but we'll also have to see if there is unparsed stuff on the line. So no, you know, if the parser is not at the end of the line yet. So if, you know, parser dot, how do we check for an equal sign like this? If parser input get maybe parser stuff is this, then, well, we have a definition that didn't get passed on the line, which means it's a multi-line definition. Which means now we can be like, hey, let's create a definition. Yeah, and definition is, and now we basically need to do the same thing that we did up here. You know, this part. So we're gonna factor that out into another method, another function. Parse expression. So we're gonna have a create definition, create def. Takes a left side. Or parse, not really. And takes a right side, which is a body, an asked body, in fact. And it's gonna return an asked expression, or rather an asked definition. And it basically does this. You know? It checks what is the thing on the left side. If it's a name, well, okay, then I'm going to return, beautiful, an asked definition with that name, and the value is Okay, true. What if you have this? This would just define a variable. A variable that, you know, just happens to have multiple, like I can imagine you do some weird computations in here, and I think the last value here should be what this variable like resolves to, what it evaluates to. So what we really want is to write this multi-line thing that this ast body should just be an ast expression. Yeah, let's have a body in here. Which is an ast body. Yeah. Okay, so in here, wait, in here, create def. Yeah, if we passed some value on the right side, how is that? When we have an ast body. Oh, I see. Right. So create def accepts a right thing, and that's just an ast expression, which will be a body in the case where multiple things, where there are multiple lines inside a function, which means the ast fun has an ast expression as the body. That makes sense to me, at least. Okay, so in here we basically just say, well, please make a call or create a definition. Almost the same thing. So yeah, basically the expression is the left thing. Oh, I just hear my PC fans lighting up. I don't know why. Well, too late. So the thing is, up here, oh god, we have an ast expression which contains a body. Wait, no, we have a fun which contains an ast expression which contains a fun which contains, and so on. Yeah, this is a recursive structure. So that, hang on, let me get syntax highlighting back. Okay. Yeah, as soon as you create a recursive type, the tooling is like, whoa, let's analyze that. Like, let's analyze that, and it takes all of the CPU it can get. Well, anyways. Okay. Cool. Yeah, we create a definition, and we want to call create def down here. So if there's an equal sign at the end of the line, then we want to create a definition with the left part, which is the expression, and the right part, which is an ast expression body with an ast body, with expressions which are the children. And up here we can say if there's, we pass an expression and then we're like, oh, there's an equal sign and an expression coming after that. Well, then we want to say create a new expression, please. Like create a def, where the left part is the existing expression and the right side is the value. Cool. Basically this. Look at how small this thing becomes. We pass an expression, then we pass arguments, optionally wrapping this in a call, and then we're like, yo, if there's an equal sign coming afterwards, we want to create a definition. And create def is down here. It gets the left side. If it's a name, everything's fine. We can just be like, yo, the value is the right side of the expression. And if it's a call, then things get weird. Then, we need to check that the parameters are all strings, that the name, that the receiver is a name, that, and then this is a definition of a name where the value is an ast function, and the body is an ast expression, namely the right side, just like that. And that's it. Oh, and put on heap. Right. Yeah, that's it. Okay, cool. So this is, quite simple. We just, if we have something like this, we just pass a call on the left side. Then we're like, oh, there's an equal sign. So then we inspect this, what we passed before. And if it's just a single name, this becomes a definition of a value. If this was a call, then we ensure that this is a name and that these are all just strings and not, something like this. And then we define a function where this is the body. Okay, we still need to check down here because, oh, wait. Oh, children is already an ast body. Oh, that's convenient. Nice. This is invalid because this is an expression, so we need to create an ast expression def. And down here we need to parser.cursor is parser.cursor plus 1. Parser consume white space, and we need to ensure that the parser cursor is at the end, so that this is parser input len, or there's garbage on the line. There's additional garbage on the line. Oh right, this has to be mutable. Okay. Alright, we can actually do this on, like down here. We have a parser for the line. Yeah, here we advance the cursor, but then down here everything on the line should be consumed. Additional garbage on the line. Yeah, no, we're not gonna print that. We're just, oops. Yeah, I don't handle ast body, that's true. So if there's a body, actually we're just gonna print the body, right? Print the body with our indentation. Beautiful. Oh, this doesn't work. Why not? Because this is a reference to an ast expression and not an ast expression itself. Okay, there is additional garbage on the line. Sure. What's the garbage? In which line? That's the age-old question. Let's print that. Parser input dot substring from parser cursor to parser input len, please. Oh god, this is, yeah, like this. Additional garbage online, foo. Oh. Yeah, the only place with foo. Why, though? Yes, there is an equal sign. Oh, yeah. We need to consume the equal sign. Okay, so if there's an equal sign, we basically want to only consume it if there's an expression coming afterwards. So we basically want to say var cursor, parser cursor, and if we pass an expression, everything's fine. Otherwise, we reset the parser cursor to the cursor. Let's call it cursor at equals sign. Otherwise, we don't consume the equal sign, so we do that. Great. And something else I'm missing, something else. Right, we need to advance the cursor because parser cursor equals parser cursor plus 1 because we want to consume the equal sign. That is certainly a thing. Okay, so we have 1, 2, we have, oh wait, that's the int. I have no idea what's going on here. Oh, I may have some idea. No, not really. What's going on here? Is it like failing when it tries to print the call, or I don't know what's going on. Segmentation fault. That's like, yeah, that's, you know, that's memory unsafe language being memory unsafe language. Okay, so let's maybe print converting post.line keyword, so we have quotes around that, to ust. Okay, so the moment we say here's an assignment converting, well, we'll have segmentation fault converting to ust for equals something. So the way we do that is we have a parser, we parse an expression which works, then we check what are the children, we parse those, yeah, initial, I don't know, self-contained line, horrible name, you know. Basically I want to see the expression that's, oh come on, yeah, that makes sense. Well, okay, let's do it like this. So we convert vec equals foo to ust. So then we parse, you know, this line first as a self-contained unit. And it's already a definition. Yeah, definition of a vec equals foo. Beautiful. But then we're like, please do stuff. Oh wait, is it like during printing? Or is it during parsing? I should check that. Parsed, ast, printing. Okay, no, it's between that. That's like, whoa. Initial self liberatum. We have the children converted to an ast. And then we're like, let's advance the cursor. Recreate a definition. I'm just gonna only print this maybe. Okay. That's bad. Parser input. Can I just print the parser input? That should work, right? Online vec equals foo. Okay, so let's print the cursor. And if this is like -5 or something, because it's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I suppose it's at the end, perhaps. So parser cursor to parser dot input dot len is what we would have printed. The substring, oh, from 10 to 9. Well, that's not good. How can that be? That doesn't make any sense. Because I know it's only 1, 2, 3, 4, 5, 6. It's only 9 characters long, yeah. So it should, like, okay, it shouldn't print this, like it shouldn't do a segmentation fault. That's for sure. That's bad developer experience, but that's another topic. So why doesn't this why does the cursor go this far in the first place? That's what I'm wondering. Maybe let's just initial and then we're gonna print the cursor. Okay. Converting foo to ast. Boom, and the cursor is already 10. That's wild. Okay, parse expression. You do something bad up here. I can sense that. Oh, right here. We just say, well, let's add one more. That's one too many. Okay. Yeah, let's do it like this. Oh, okay. I would have said beautiful, but this is still weird. still really weird. Okay. What's going on here? But that's only, you know, okay, at the start of every expression, we print indentation. That makes sense, I think. Yeah. So here we print indentation. Makes total sense. For a definition, we print, yeah, the indentation up here. Totally makes sense. Yeah. Then we have a function. A function where we basically say, well, we have parameters, sure, and then we just write the function body, which is an expression which goes down here, which writes the actual ast body, which is here, which prints the individual expressions. Where are those coming from? Like, it should be 4, but I think 1, 2, 3, 4. Oh, right, because body is an expression. But if we have a body, then all of the individual expressions will already print indentation. So, you know, if the expression is not a body, by the way, you saw the if-is thing, I don't know where, but somewhere. Yeah, this right here. You can also use is as basically an operator that checks if an enum value is of a certain variant, and that just evaluates to bool. That also works. So for everything except bodies, we print the indentation. Yeah, look at that. Okay, so we call add with 1 and 2. We call add with 1 and 2. We define add as a function that takes a and b, which defines a vec as foo, and then returns bar. That's nice. That's basically exactly what we want to do. Okay. Wow. That is like super cool. I like that. Let's maybe, you know, the built-in add, which just automatically exists. Let's do something like this. Okay, and now let's actually start on making this program do something. So we have the ast, which is basically a representation of the syntax of our code. Okay. Yeah, I'm gonna do a quick break. So let me share the amazing iPad break thingy. Oops. Like this, or rather like this. Just getting some more iced tea. Okay, I have new iced tea, so we can continue. All right. Where were we? We have parsed an ast, which is a beautiful thing. And now we want to analyze it. Yeah. So I think it's time for our next intermediate representation. So let's create a new file called, what's it going to be? You know, finding names for all of these stages is kind of not difficult, but so, you know, tedious. It's like, basically these are nothing but you know, but fancy, like ast or ild doesn't have to mean anything. It's just an arbitrary name that you prefix for those, before those things, and that you use everywhere. So basically now we want I think that's an unordered you know, where the names are basically resolved. So I think the next step would be to figure out that when we call add here, that this refers to the add that is defined down here. Also, I should maybe mention this. Like, thinking about name resolving in general, I want to be able to have multiple definitions like this, which are like the order doesn't matter, right? For top level things, the order in which they are defined, so who cares, right? But inside of bodies, like inside of functions in particular, I want the order to matter, because here I want to be able to be like, hey, print, or like debug stuff, I don't know, debug high, or I don't know if I say crash. You know, I have some check that A equals B, like this perhaps, I don't know, and then I'm like, if that's true, I'll assert, right? And if that's not true, I want to crash. So those things down here, that should only be executed if this up here didn't crash. So the order of execution matters. Outside of functions, it doesn't. And yeah, so I also, similar to how Martinaise does it, by the way, with the content, I want to allow shadowing, so that I have one variable of some type, in this case like slice of byte, I think, and then I want to be able to define another variable with, like, which is totally independent, can have a different type even, of type string in this type, in this case, and it should be able to depend on the value of the old variable, because, you know, something like this, I see this all the time, and I write this all the time, because once you get used to this, that this makes sense, then it's, you know, you have this weird type which is very, I don't know, very generic, and you need to assert certain things and make sure that you know, you need to extract some information, some values from that. Then you can just do that and give it the same name. Right, so cool. I think, so yeah, I want to allow shadowing inside of functions, I think, because the order matters, but not outside of functions, because if I would write this right here, there's, like, the order doesn't matter, so if I write bar up here, you don't know which bar to choose. But inside of functions, you can do that shadowing, and you can do, you know, do stuff like this. Okay, so let's think. We have we have code in here, in those functions. And now we need to have a stage similar to this one, but the names are all resolved. So this basically just represents the file. But for example, if when the names are resolved, I actually want to, it should be more semantic, more operate on the meaning of the data. And it doesn't have to represent the structure of the file. It can just be, let's write it down somewhere. Oh, we need a name. It can just be, a number of like top level definitions of either values like these, or functions like these. And having these other expressions doesn't even make sense actually, because that doesn't do anything. So I wouldn't actually allow that, I think. Yeah. And then inside of functions we have this, we can also flatten expressions. So for example, when we have, I don't know, we add a and b, and then we multiply that with a. Something like this. We can, simplify that to like a temporary variable 0 is a, temporary variable 1 is b, and temporary variable 2 is, I don't know, just the plus function. Temporary variable 3 is, well, temp2 called with temp0 and temp1, and then temporary variable 4 is the times function, and you can just go crazy on this. What would it be? Temp0 times temp3. Yeah. So that you don't have these trees of expressions anymore, but that they are turned into very simple flat operations, such as refer to a parameter, refer to a global, either global variable or global function or something, like a global definition. So this would be like, this is param R, this is param B, this is global plus, global times, this is a call. You can already see that this is similar to the ast enum. We'll have an enum that says, what is this operation? But these are not nested, but they are primitive operations. So a call probably has something like, I don't know, IDs or something in here. Yeah, we can actually, let's rename this to, I don't know, colon or this, or dollar or euro, because why not? Yeah, I'm in Germany, so no, what is no? I don't know, something like this perhaps. Well, yeah, I don't know. They basically just have IDs that refer to other expressions that are defined before them. That's the idea. Resolve names, resolve, turn expressions into like a flat series of things. Yeah, cool. Cool. Mm-hmm. Okay, so let's do it. Right, we still need a name for that. So in here, the expressions, they don't have types yet. I want to, like I said in the beginning, that functions are not compiled just like this, but they are only compiled for specific types of arguments. So if you compile format for int, then you get something that contains a function that contains only this, and the rest is removed basically. And all of those intermediate values also have types. But in this stage, we are not there yet. So this would be untyped. It would be a flat series of instructions. It would be, you know, yeah, the top level functions, they don't have an ordering. They're probably in a map or something. Just need a name for that. And the way I usually go about this is to name it like here or something, which I guess we're gonna do here as well. Here as well. Yeah. So the way I usually name my stages is, hang on. Oh no. Yeah, something like this. Oops. Yeah. So I have a source code and then a concrete syntax tree. Here called it abstract syntax tree directly. But then basically you have a high level intermediate representation, then mid level, then low level, and if I need more than that, you just, I don't know, add extra very low, the vlir or something. And it doesn't really matter how you call these, it's just, can be anything. Yeah. Actually, we could call those something funny. Like, could call them the ast, for example. We could say for example, it would be cool if we have something named with P and O, so we have the toast, right? Oh, and then here you have a slice of toast, for example. That would be that would be amazing. That would be so amazing. Okay, let's do that. Let's rename this to toast. Oh, this is crazy. Yeah, we have the toast. I'm not gonna do that here. So toast. Oh, crazy. Toast. Yeah. Do we need a body, actually? I don't think so. I think we can just replace this with, a slice. And the whole, the main thing can also just return an expression directly, which contains a body. Because we added the body when we didn't have this yet. But now that every expression can also be a body, we can just say, well, let's remove this and just call this toast. Okay, and these things, we're gonna call them toast too. Great. Yeah, toast body doesn't really exist. Instead, oh, this is great. This is a slice of toast. Yes. Cool. A slice of toast. I mean, amazing. Amazing. Right. So, yeah, slice of toast. It makes sense that this is called body. And then we just do for each expression in there, we do stuff. So when writing a toast, we do this. Perfect. We have a parser, which by the way can become brought down to a single line. Maybe toast, toast call, toast, toast def, toast, to toast, not to ast. What's an ast even mean, right? Okay, to toast, and this returns a toast, but it returns toast dot body with the expressions. Great. Yeah, there are probably some things we didn't catch. Right, for example, in the main file. In the main file, this is called toToast, and well, and this is a toast. And looking for toast. Toasted body. Try to create toast body with toast, but it needs a slice of toast. Indeed, it does. 136 here. Children is, oh yeah. Look at how much easier the code gets, not the toast. Yeah, this is just that. We can do nice. Toast call args as children, which is a toast. Yeah. Oh, right. If it's an empty toast body. Oh, right. Now we can do ilt. Yeah, ilt dot children dot is not empty. Yeah. Args is children. Well, that's unfortunate. Oh, yeah. Let's do it like this. To toasts. And not do this down here, but instead wrap them where necessary. Why isn't this working? It.children.toToast. Incorrect. Why? Oh, right, because it's another file. Yeah, the tooling only analyzes open files. Oh, but we should be able to do this, right? Turn the entire ild to body. 133 down here. Turn the children to toasts, and then we say, well, yeah, this is a definition of toast body of that. Yeah, and here we can check that, and then do this. Okay, this is nice. Okay, writing things doesn't work. Where does that work? In toast, this call doesn't work. String with a toast. These definitions have the same name, but arguments don't match. There is not one for toast. There is one for slice of toast. Write slice of toast. Write toast with an with an indentation. Only with an indentation. Okay, but that's what we want to do here, basically. We want to write the toast with indentation 0. Yeah, if this is a body, we write the body with the indentation, which means we write all the expressions with an indentation. Nice. What's going here? Toast body. Toast body. Oh no. We can just say write the arguments. What? Okay, converting empty expression to as expected expression. Right. Because this is an empty ild. An empty ild is, like a special case. If ild.line is empty, then this is the root of the tree. The eld doesn't any other empty lines because they got filtered out. So in this case, we just return, eld.children to toasts and wrapped in a toast body. Okay, yeah. What's going on here? All right, I just wrote into this file. Well, yeah, this doesn't work. And this, oh yeah, I should allow symbols for. Okay, this is fantastic. Bears is bar, foo is 3, bar is 5, bar is 2. Well, yeah, that doesn't make any sense, but it gets passed. Add is a function that takes an A and a B, and then it calls add, well, build an add with A and B. Beautiful. Passed toast. Yeah, I'm gonna remove the debug printing here. Yeah. And in the Kamin, I'm gonna add a new line here and here, and actually, let's rather do that for them. Maybe not. Okay. Hello world, and then we have the eld, and then toast. Okay, cool. So, next up, the next compiler stage. It would be nice if it's something, breakfast themed. Like, maybe I'm gonna rename the language to some breakfast name as well. We have a toast, which is amazing. The next is the next is no longer tree, right? Because all of the nodes have IDs to other nodes. And it can be that you have a definition and then multiple other definitions depend on that one, and it's more like a graph. So we could say this is an expression guided graph, for example, an egg. Yeah, and we still need something for eld, but that's difficult. Yeah, I'll think about it later. So this is definitely valuable, have each compiler stage named after some breakfast ingredient. Okay, so the expression guided graph will be, something like the toast, but not really. Oh wait, we haven't even thought of an acronym here. Like, this is amazing. The egg. Well, totally awesome. Totally well, future work. We have the egg, which won't be this actually. So let me just do it like this. Okay. So an egg. What is an egg? An egg is basically a representation of a file where the names have been resolved and where complex nested expressions have been flattened into a series of very, very simple expressions, such as calling a function or stuff like that. So the egg basically just contains the definitions, which are like top level definitions, and they are mapped from a string to an egg def. Beautiful. Beautiful, yeah. Yeah. Now, what about an egg def can either be just a value or a function. So an egg def can either be a value or a function. Yeah. Okay. I guess let's walk inside out to start with this. So we will at some point have an egg body, which is what a function contains, but also what a value contains, because back here we can see that values can also be complicated. They can have like intermediate values in here, and they evaluate to the last expression. So yeah, this is also a body. Everything that's an expression, possibly complicated as expression, which with nesting and everything, gets converted into a flat egg body. And okay, so this is going to have a list of expressions with what? Expressions with which is a slice, I think, of egg expressions. Yeah, I like that. Yeah, okay. So then, yeah, we have egg expressions. So we have integers. We don't have names, no. Instead we have basically references to other egg expressions. Yeah, and I think egg expressions can only reference expressions inside of the body that they are in. So this is like a, just an index into that list. Okay, we should, like, this is horrible API design. We should, this is very error prone, because you could put a 2 in there and, this doesn't tell you anything in the end. So I think it makes sense to have an egg ID or index or whatever, which is just a fancy int. But then this can reference an index ID maybe. Yeah. Cool. Okay. So an expression can be an int. Yeah, it can be a reference to an egg ID. Come to think of it, when would you ever use this? Like, sure, you need some way to reference, you know, like a parameter with a string, maybe the parameter name, to be like, yeah, this expression is the parameter, and then later on other expressions can refer to that parameter. Okay, you know what, let's scratch that. Let's just write an example. So in here, I think what this should turn into is something like this. This is parameter A, this is parameter B. Then we have, you know, built-in add is probably defined somewhere globally, but you know, it's basically defined by the compiler. And then here you say global built-in add, and then you call that global with those two. Yeah. But you never need to have something like this. Or maybe you do, because, let's say you have, I don't know, a foo defined in here. Then you do something, you call another function, and then this entire body evaluates to foo, which is the last expression. Okay, but we can say that a body always has a return ID, which could then be, you know, if this function would just return A, although it adds them, it could just return that, like this. So a body has a list of expressions, and the ID of the expression that it returns, which doesn't have to be the last one. But because we have this, we don't need to be able to reference previous IDs. Because instead of using the reference, you would just use the original ID that it points to. You also need to reference globals, yeah, and call them. And that's basically it, because defs, they get, you know, they get added to that map. Funds, yeah, let's not have funds first. I think later on we need functions inside of functions that can capture things and so on. But for now, let's just get, you know, let's just have top level functions that can call each other and so on. And you know, closures are nice and useful and so on, but you can compile closures to normal functions basically. Okay. I mean, this already looks so much simpler than this, right? Because it's more structured. You have the inside of a function that basically can't happen a lot. And all of the functions are organized up here. That's pretty great. Oh, right, a call. Of course, this is, you know, an egg call, and we don't need this. It has a receiver, which is just an egg ID, and the arguments are also egg IDs. Okay, beautiful. So back to the egg definition. Yeah, an egg definition can be a value. in which case it only contains a body that can calculate it. Right, and egdef refers to egg_fun, but that type doesn't exist. True. True. Because an egg_fun has parents and it has a body. And that's basically it. Yeah, it's basically a function that can have parameters. Yeah, a function is just a body that can depend on parameters. That's actually, yeah, I think that's it. Cool. Do things a little bit more compact down here. Okay. Yeah, I think this is nice and tight from the organization, you know. You have the general like structure of the program up here with definitions and functions. This is the body stuff with IDs and the body itself. And then you have expressions and related structs. Okay, let's, I guess, first print them. And we can import that file. Import toast, import egg. And this still needs something to do. Flattening. Okay. Is toast to egg. Fantastic. So we need this to egg down here. To egg dot toast returns an egg. And we need a write function that can write the egg. So yeah, let's do that first, because that should be relatively easy. We don't even have like indentation or nesting anymore. So for the egg, we just go over the definitions. So for each def in egg defs, we basically just print the definition. Yeah. Oh wait, we print the definition key. So this is a map, so this returns like map entries which have a key and a value. Yeah, so this has a key. Yeah, let's maybe do that directly in here. And then we switch on the definition value. If it's just a value with a body, we write that body. If it's a function, we first write the parameters. And then we write the body of the function. Yeah, I'm gonna add a new line up here and here as well. Or maybe not. Maybe not. No, I'm just gonna leave it like that. And the body starts with a new line. Sure. So writing body, an egg body. What it basically does is that, okay, you know what, I'm gonna add a new line because it's kind of unclean that that write method also it prints white space around it. I know for the ones that take indentation, it's kind of expected, but otherwise, yeah. So for each, the body has expressions. So for each expression in, wait, what did I write here? Yeah, for each expression in the body, we basically just write the expression, right? So we just say writer dot We have indentation, which is always like 2 spaces maybe. Oh, the ID we want to write. And I'll try to, oh, come on. I'll try to print it something like this. You know, IDs just have a colon at the beginning, and then the expressions, they are not nested or anything. So they can just write what kind of expression they are, followed by arguments or other data. But we need the index. So there is a iter.enumerate, I think. Something like this. Yeah. And then this is an enumerated thing with an index and an item. So we can do that. And we print a new line after that. And then at the end, we print what the body returns. So body returns, which is an egg ID. Okay, so how do we write an egg ID? Egg ID, we just write colon and then the int from the ID. And maybe let's put that in the same order that they are up here. Okay. So the last part would be writing an expression. So an egg expression, which would be to, well, it depends. We need to switch over what kind of expression it is. And for each of those, we're gonna do something different. So yeah, for ints, we just write int and then the int. For parameters, we just write param and the parameter. Oh, okay. For globals, we just write global and then the global, and for calls, well, calls actually a bit more complicated. We write call, and then, you know, call the receiver, which should be an ID, yeah, and then the arguments. So for each arg and call args, we print the argument. Okay, so next we can print an egg. So converting toast to egg, that's that's like magic. Right. We have toast. We want to have egg. Just a reminder how a toast looks. Right. So we go through. Okay, so hang on, the toast is a body. Right, it depends on the toast. Of course it does. Does it? No, the toast is always a body, like the top level toast. Yeah, something like this. Top level toast is not a big body. Okay, and then we basically just and up there in the corner. I hope I didn't. Oh, I can move myself down here. Oh yes, I'm not even hiding any source code. That's neat. Okay, so the top level toast is not a body, which is fine, which is expected. So now we have the definitions, and yeah, we kind of need to go over them. Alright, so better for, I don't know, toast and this, do, and, you know, a bunch of stuff. Oh. And we have definitions, which is a map from string to egg, no, sorry, to egg def. Right, and then in here we add to those definitions, and in the end we return an egg with those definitions. Beautiful. So now the only question is, how do we map toasts to egg defs? And we basically need to switch over what that toast is. If it's a definition, oh right, we can say this has to be a definition. Or, you know, we panic, top level non-definition. Because something like this would basically panic, because this doesn't make sense. For now. Like, for now this will panic. Later on we'll probably want to show a compiler error and, you know, not crash the entire compiler at that point, but yeah, for now, let's just get to a working state as quickly as possible, and then we can always flash things out and make them more error resilient, more robust, and so on, but right. Okay, so this doesn't make sense. This should panic. And I can even print that here. I can say toast. Nice. Okay, so we can print a toast. We can then what can we do? We can check what's the value of that definition. Yeah, if it's a function, that's fine. If it's not a function, that's fine, I guess, but yeah, let's maybe do that, right? Right, we have toast def, and a toast def has a name and a value. So we have the name. Well, the name doesn't really matter, does it? I don't think so. We want to switch on the value. Yeah, if it's a function, then we want to, you know, lower that body of the function into to egg of the function. Often, what is it? A toast fun. Beautiful. So a toast fun gets converted into an egg fun. Hang on. Yeah, into an egg fun. Beautiful. Cool. An egg fun, yeah. If it's a fun, then def value. If it's fun, then it is an egg fun. So this is a egg def.fun of, you know, fun to egg, which calls this down here. And otherwise, we just lower it directly. Yeah, and that's a to-do. Yeah, there is actually a to-do function, so this will just panic if it's reached. Okay, all right, and then down here we say devs dot put name value, put that into the map. Okay, so the question is, how do we lower this, and what do we do in here? And it's quite similar, I think, because in both cases we want to have a single body, and we have this toast, which is just this, but can be like a complicated nested expression and so on. And what we want to do is basically have a body and iterate, like traverse over the tree, and each of those nodes can append something to the body. So we create a single body to egg, and those toast things, they can append to the body. And a body is an egg body, which is this, which is not really reasonable because we need to have something more. Let's create an egg body builder, maybe, where this is a vector and it doesn't really track what it returns. I mean, we don't really need the builder. We could also just say we have a vector directly, if there's nothing else inside, right? Yeah. And this returns an egg ID. That's the cool part. Yeah, that is really cool. Okay, yeah, maybe I'm just anticipating. on the builder, I want to have we can have a builder with a push function, which is similar to pushing things to a vector. But we have a builder, and when you push an expression to a builder, you get back an ID. So the ID is just the index into where this expression will be. And well, that's just builder expressions len wrapped in an egg ID. No, like this. And then builder express dot push the expression. Okay. Right. So in here we have a mutable egg body builder, like a reference to an egg body builder. And we just switch on the toast, to be honest. Yeah. So this is one of those cases where we need to handle all different, all different variants. Okay, so if it's an int, what do we want to do? Well, we want to, wait, this should also return an egg ID. Beautiful. We want to push an egg expression dot int of the int. If it's a name, we want to, resolve the name. If it's a call, oh, now it gets interesting, because here we want to flatten that thing. Instead of having a call, which is, a tree with nested expressions, we can just say, well, let's first turn the receiver into, add it to the body. So the receiver is just the call receiver to egg with the mutable body. So this will actually append other intermediate expressions to the body, and then just return us the ID of whatever that results in. And similarly, we do the same for all the arguments. So we need to store them in, what is it? Egg IDs, just, yeah. So for each arg in the call arguments, we're gonna take the arg, convert it to an egg, appending necessary things to the body, and then push that final thing to this list of arguments that we have here. Which means that at the end we can just say body push egg expression dot call with an egg call, I think, egg call, right, with a receiver and argument, which is a slice of egg IDs. Yeah, so this right here would have a receiver, which is already an egg ID, and args is args to slice. Beautiful. Yeah, definitions can't really appear here, so this will be like definition non-top. Oh, yeah, come to think of it, they should be possible. Like you should be able to define like variables inside functions. So it's more like a to-do. But this is a panic for now. Non-top level function. Yeah, and if there's a body inside of this, I don't know how. Oh yeah, you can define a variable which is then multi-line, which has multiple other expressions. So that's fine. We just say, oh, it's called body. Let's call it expos, so it's not clashing with this one. So for expo and expos, oh, actually, so, to egg with a body. Now the thing is, I want, for something like this, I want the body to evaluate to the last expression. And this is actually what we're writing right now. When we find a body, we need to evaluate to some kind of egg ID. And, well, what egg ID is what we decide right here. We want it to evaluate to the last egg ID. So the way we're going to do that is by having like a variable, what is the last ID, and it is set to none. By the way, none is like from in the, I probably used this already before and didn't explain it, so sorry about that. But there's this maybe type, which is similar to option in Rust, or maybe in Haskell. Yeah, it says it right there. So yeah, this maybe is just an enum that is either some or none. And the, let me move things over here. Yeah, there's either some or none, and there are functions that can create a value, like the sum variant or the none variant. And these are like global functions. So I already used some of these. For example, in the parser, I think I used, where's the toast? Yeah, and here, like some, because it returns maybe. And none when it doesn't, like returns the none variant. Yeah. Then again, honestly, I'm not sure who's watching these videos. If those are people that are like experienced in Rust, or if it's just nobody, that's also fine. Yeah. Okay, so this will be an egg ID. And here we say the last one, we just set that to this. And then at the end, we just return last, or if the body is empty, what do we want to do there? We can say we want to disallow that, maybe. Although that's kind of weird. Actually, let's disallow that, and we can allow that later on. So, empty body. For now it's an error. Maybe, it won't be in the future, but for now. Oh, right. So, about that. File names can be weird. So, the way import works is it takes the entire rest of the line as a file name, because actually now that I think of it, you could have a file name that contains like this pipe, right? I'm actually not sure. But it can contain spaces and so on. But so maybe. Well, anyways. Yeah. Okay, so to egg. Yes. 60 here. Well, true. Yeah, we somehow need to use parameters somehow. And then, you know, the function body is an egg body. Which is just a slice, I think. Let me check that. Function body is toast. Oh, right. It's just a normal toast. So we can just say, yes, I know. Say to egg on a function body. So you can create a body, which is an egg body builder. And we're gonna do the same up here. So let's add, you know, kind of a constructor or something, but not really. Just a function egg body builder which returns an egg body builder by creating an egg body builder with expressions being an empty vector of egg expressions like this. Oh, I can't even. I think Martinaise has type inference in some cases. I'm not sure if it works in this case, but I think it does. Like of, you know, only type inference of return values. You can't infer the arguments of functions. And of course variables are always inferred. You can't even specify a type there. Okay. Right, so in here we just say we want to create an egg body builder. Yeah, and for builders you usually take, yeah, I'm just going to take the reference, so I can just do to egg with the body. And then this will also have a finish function, which then returns an egg body. So, oh wait, finish with ID. Returns an egg body with expressions, I think it was. Yeah, expressions is, well, builder is an egg body builder, ID is that, and returns an egg body. Expressions are the builder expressions and returns the ID. Right, so we create a body, then we lower that, and then we're like, okay, body dot finish using that ID. Beautiful. And we can do something similar up here when we have not a function but just a value. I like that. I quite like that. This doesn't work. Okay, to do with a string. Well, that sucks. Okay. Why doesn't? I want that to work. I'll add a to-do function to the standard lib. Oh, where is it even defined? Probably in core, maybe, perhaps. You know, there is no jump to definition on functions. That's annoying. Maybe process. Asm, maybe asm. Yeah. Oh. Yeah, so Martinaise has its own memory layouting and calling convention and so on. I'm not sure how much of that is needed in this project, but okay, we want process would probably work because exit is defined in there, so no panic, and to do, nice. So I also want to do with task. We still need to do this task. it never returns. Yeah, and it just panics. To do, and the task that you still need to do. Beautiful. Beautiful. So now this should compile. Almost. So 65, that's up here. Last expression of the body doesn't match stuff. Body.finish. Right, that only returns a... Right. Okay. Yeah, that only returns body. Body is this. And then we return an egg fun, which has params, which are the fun params, and it has a body, which is the body that we have in the scope. Okay, fun is not in scope. Why is... wait, what? Oh, up here. Yeah, that makes sense. Default. Oh. Yeah, we'll just take the value. Turn that into an egg. Wait, value is not... I see. Okay, let's factor that out. Like this. Okay, sure. Put. We have a mutable map with a string and an egg definition. And we want to put in there a body. Well, that doesn't make sense. I agree. Weird that it doesn't show the error here when this evaluates to an egg definition, this to a body. That's compiler bug, compiler bug, compiler bug, compiler bug. So egg definition, egdef.value is what it's called of the body. You know, this is a bit deep even for my taste. Okay. Okay, def is not in scope, indeed, because this is defs. What? Okay. Actually, you can actually see how, you know, it first calls to egg, and then it prints egg. So now we get errors in the print functions. Oh man. Okay, expression is not a field on egg body. It only contains expose and returns. And yes, this is expose with plural s. Okay, iter on egg fun up here for param, and yes, and fun with params. Written, no, that's wrong. Oh, that's in here. No. Okay, now this got type checked, and now this is analyzed, so you can see how far the compiler got. Okay, that's cool. Oh yeah, this is total garbage. Let's go in here and clear all that up. Oh, and this actually fails. Yeah. Let's do it like this. Okay. Yeah, okay, we can't resolve names yet, which was expected. Because we have no way, like we can't do anything about that. So how do we resolve names? That's kind of an interesting thing. I already have an idea on how to do that. Yeah, but I'm gonna make a small, very small break, and then I'm gonna be here afterwards. So let's just show the break thingy. Break. All right. So the Right, variable scoping and names and so on. This is kind of a difficult topic in some languages because, you know, you have a lot of different operations you need to do. For example, let's just go through this, and let's check how variable scoping works. Basically, when we have this right here, we want to be able to resolve all top-level functions. So, you know, buzz, foo, bar, add. This makes no sense. These immediately become visible as soon as you know, in the first line of the file, basically. And then as you go through this, some more might become available and disappear. So for example, in functions, if it references a bar, okay, that's fine. We know what that is. It's a reference to the global bar. And inside this foo, okay, that also works. It's just a for. Inside this bar, here we define another foo. So the moment this is defined, this foo should no longer, you know, this this is not in the code, you know, this is just tracking what variables are visible. Now this foo should, now if you write foo, this should no longer refer to the global foo, but instead to this local foo. And I think the easiest way to do that is to just have a vector or stack of things. So bus is like, hey, this is global. Foo is, yeah, this is global. Bar is this global. Add is global. And then as you walk through this program, boom, 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 boom. If you define something like a foo, for example, you just add it to the end. So foo is a local with this egg ID 0, for example. So then when you reference foo down here, the only thing you need to do is look through this vector, but starting at the end. And then you're like, oh yeah, foo is a local function. And this overrides or shadows the outer function. And this even works when you have nested scopes, when you have a baz, a flup, which defines an A and a B and so on. You know, you just go through this function from the beginning. We have foo added just now, and now we go inside of flup. We define an A, the definition is finished. Okay, so we add A here. A is some sort of local. I'm just going to write G for, or G for global. And then you evaluate B. So, you know, B is also a local thing. And then when you exit this thing, maybe let's say you evaluate to B, for example. Here you can reference B because you just look from the end of this vector or stack of visible things. And then when you exit a variable scope, you just have to remove all the variables that you added. So basically, before entering a body, you save how long this vector of visible things is. If you define variables, you just append to that, and when you leave a body, you just trim it down to the original length. So yeah, we trimmed those in here, but we defined a flips variable. So yeah, I think this should work quite elegantly. So yeah, this then goes down here, and then boom, this ended, so we're gonna remove everything up until here, and then you go into the next function and start over. So let's implement that. Let's maybe create, you know, I like that we have the egg definition up here, and you know, the write calls, and then down here we have everything related to the conversion. So let's define, maybe before the conversion, variable scoping, something like this. And we have a struct which is vars, maybe, you know, the visible variable scoping, and then we have, you know, converting toast to egg, tracks which variables are in scope using a simple vector. Yeah. When new variables tracks which names are in scope using a simple, yeah, when new names are defined, appends items to the vector. When names are referenced, walks the vector from the back and searching for the name. Variables that are defined later shadow previously defined names. I'm gonna write names because, you know, it's variables and functions, so I think this is the more general term. When bodies are visited, maybe compiled, I don't know, save the length of the vector before entering the body. When exiting the body, trim the vector to that length. All names defined inside the body automatically go out of scope. That's the idea. So we have vars. Yeah, and it's gonna have basically a vector of vars. What's the var? Well, name, scope, name, scope. I think scope is fine. That's how they're usually called, so yeah. Yeah, name binding. This is horrible, but okay. So we have globals and we have locals. And yeah, you can create a new scope. Which just, you know, let's do it like that. Creates vars, vector of name bindings. You can define a new name. Alright, they also enum name bind. Oh, wait, it's a struct. Also needs to contain the name, of course. And then the value name value something like this. Yeah. Define a name and a value. on a scope, which will be a mutable scope, and it basically just appends that to the vector. So scope dot vars dot push a name binding with a name and a value. Yeah, exactly. And then there is a lookup, resolve, or yeah, lookup is nice, I think. Takes a scope which is not mutable, takes a name, and it returns a maybe of a name value. Yeah, what it does, it just iterates the thing from the end. So for binding in scope.vars.iterref, I think that exists. Do if binding name equals name, then return binding value. And down here we return this, and up here we need to wrap that in a sum. Cool. Okay. Cool. Before entering body, we also need to be able to snapshot the length. Scope is not really a good name for that, because the individual, sections in which a name is visible, they are called scopes. But this is one global thing that tracks which variables are visible, so let's call it visible maybe. Yeah, I think something like this. Oh, that's okay, yeah. Oh, right. Visible.vars.len. Beautiful, but not really. And then there's restore, which takes a mutable, visible, and a snapshot, which is a visible snapshot, and it just says visible.vars.len equals snapshot.vars.len. Okay, so we have a struct with a vector inside. You can create a new struct. You can say, hey, I want to define this name to be this value, although it's not really a value, it's just either a global variable or it's a local ID, but who cares, right? Okay, and you can look up a thing which basically iterates this vector from the end. Right, and returns a matching thing. And you can also say snapshot, and that returns you a thing that you can then pass to restore to remove the variables that were defined since you called snapshot. Oh god. Okay. So down here, visible is visible. Yeah. And then whenever we call to egg, oh wait. Yeah. So this has to be a body. So I think it's easiest if we first go over this body. basically do this. And then we can unwrap that down here because we already checked that all of them are definitions. And then we can say visible.define the definition name. Please define as, you know, name value global of that name. Yeah, something like this. And of course this has to be mutable. Nice. Okay, then in here we can say with the value, and we just, you know, we have a snapshot. We make a snapshot. So snapshot is visible snapshot. And then down here we say visible.restore the snapshot. And this has to be mutable. Then we can in here just pass down visible as, you know, like a mutable thing. So this toEgg function can accept visible being a mutable visible thing. And similarly down here, down here, yes, so this also needs to pass visible along, and wherever we call visible we need to pass that to those recursive calls, because that's the way we roll. Okay. Yeah, we have this. The definitions are all. Yeah, we can define something now, because that just means, you know, defining a local variable just means we evaluate the value of that. So the value is def.value.toEgg. Body dot. Oh, I don't even know. Body dot. No, body invisible. Yeah. Body invisible to egg. This doesn't work because. Yeah, that doesn't make any sense. But this makes sense. So yeah, and then in the end we return that. But before we do that, we also add it to the visible thing. So visible dot define def name the value, please. Hang on. Visible name. No. Name value dot local value. Something like that. That's beautiful. That is really, really beautiful. Kind of. And then when resolving a name, we can say visible dot lookup the name, please. Or we panic, unknown referenced name. Yes. Binding? Not really, but okay, yeah. Binding is such a I think I'm gonna remove binding and instead have just a tuple, you know, the name and the name binding, and I'm gonna call the value binding, just, you know, to make this not at all confusing. But it's less names, less concepts that you have to worry about. Yeah, this is just this instead. Instead of creating a name binding, we create a tuple, and there's a function for that. By the way, a tuple is just a struct that contains two fields, A and B. There's also tuple 3, which contains A and B and C, and I think tuple 4, which contains other things. Rev iter. does exist. Oh, it exists on a slice. Okay, sure, let's turn that into a slice. Nice. So the name is A and the binding is B. The value is B. Yes. Okay, so binding is that. That makes sense. And then we basically want to switch on that. If it's a global thing, you know, is global, then we say body push egg expression dot global with that name. If it's local, oh, now it's interesting. Because now we can just return the local ID and we don't even need to add anything to the body, right? If you add I don't know, you call add with foo and bar. When you want to evaluate foo, you know that somewhere before there's already an expression in your body, something that says, well, I'm going to calculate some stuff and I'm going to assign that to the value foo. Then whatever the ID of that expression is, you can just use that here and use that as the argument to the call. Okay, yeah, let's just see what happens, I guess. Oh, yes. This is super cool. I mean, these things, they get resolved and built in add. That's not found. And that makes total sense because it doesn't exist. It's not actually defined in the file. What? Okay. So, where do we add that? Like toast should just represent the content of a file, basically the source code. Over time, I think we could also like parse comments, for example, and add them in the toast, and then use the toast for formatting files. So this should really just represent what you wrote, not one to one, like, but you know, roughly from the structure and so on. So the egg should contain the built-in functions. So we need to somehow, you know, hard code them right now. How can we do that? We have the visible things, we convert them. Yeah, right here, I think. Yes, we have those definitions. And then we also want to add built-in definitions. So let's do that. How do we do that? I think we can create yeah, I'm just gonna hard code it for the built-in add. So the built-in add is gonna resolve to a global name binding of built-in add. Yeah, something like that. And you know, this is like a very magic function. So I'm gonna just prefix it with add. You know, in Zig, built-ins have an add at the beginning. Here they don't really. But if you define your own built-in add, for example, just now, well, we'll think about that later. Unknown reference named A. Oh. We have a function. And the call references A and B. And of course, those don't exist yet. That makes total sense. That's amazing. So, yeah, and here we need to define those. Ooh, wait. Yeah, not in here, but when we say fun.toEgg, use parameters, yes, that's what we want to do. So we have the body, and then before converting the body to an egg, for each of the parameters, we add something to the body. So an egg expression dot param with the name, and that returns an egg ID. And we also add that to the visible thing. So visible dot define param as that. This doesn't work because it expects a name binding. Well, yes, this is a name binding dot local. Nice. I'm really interested. Whoa, look at this. Okay, yeah, the new line stuff doesn't really work yet. So let's fix that. But apart from that, that looked pretty good. Okay, so we have the fun body. Right. So between those definitions, we want to print new lines. Like this. Okay, so the egg is this. Wow. Okay, let's open it in the background and look at it. Whoa, so they are not ordered anymore because those are top level definitions, right? And the baz is just bar. So baz is, that's the global bar which it references, and that's also what it returns. For the foo, it just creates a 4 and returns that. What? The bar thing, this is super cool. It just creates a 5. Then it creates a 2, it creates a 3, and then it creates an add, okay, sure. Yeah, and then it creates 1 and 2 and calls that, okay. Can I also say create, add foo and floop? And maybe I want to, that's pretty cool. Okay, you see, it creates 5, 2, and 3, and even though these are in different, scopes, there was this A right here is not even available down here. Oh wait, let's do this even. Yeah, the call here, it just calls add with the 5 and the 2, which this floop evaluated to. So all of these, names and interactions and so on, they don't exist anymore. We just have numbered expressions. So this is more like a graph of expressions. There were no namespaces or scopes or anything. Everything got flattened into this. And right in the end, it returns foo rather than the result of add, which means that this body has the body has a list of expressions and the returns thing, and the returns thing just says, well, it returns 0. That's crazy. Oh, and look at this. We have a function with parameters, with a and b, and then a built-in, and then it gets called. Nice. That is pretty cool. You have complex functions and they just get flattened. Cool. Okay. Small break. Just for drinking. Okay. What's the next step? I mean, here's an extra space. I mean, that's... Yeah, don't need that. Don't need that. Okay, but apart from that... Wow. I don't even know what the next step would be. Probably... I think we're ready to compile functions with types, right? I think so. Yeah. Ooh, okay, new compiler stage. New compiler stage that takes this and specializes it to specific types. For example, the add function. We want to find out, hey, what's the return type of this if you pass an int and an int. Oh, crazy. That is crazy. Okay, what's the name? Oh god. I'm gonna get another iced tea. Okay. So the thing is, this is a stage that uses, you know, like the types are resolved. So it's basically a stage that uses resolved types. And it's still a graph. So it's a graph using resolved types. I mean, I don't know what the Yo stands for yet, but you know, graph using resolved types. Your own graph, it's not optimized, so optimized doesn't work, but your oh, graph. Your own graph. What are adjectives that start with? I mean, I still need, you know, O is a weird letter for adjectives with O. Oh, look at that. You're odd. That's you're oily. Okay. One or only. Maybe that works for some of those. Hang on. Totally. Oh, well. Totally okay. Abstract syntax tree. Yes. Nice. Oh man. Your own graph using. Yeah, why not? Alright. Ornate. Also very nice. Maybe for the syntax tree at some point. Well. I mean, obvious is also nice. Your obvious graph. Official. Oh, I like that. Your official graph. The use of times, sure. So we have the yogurt. How does that look? I mean, it's basically the same as the egg, right? But different. So I think it's a struct. Yes, a struct with all the definitions, but it's not from, you know, the name in the file to some definition, but rather from a representation of the signature to a definition. So I'm actually gonna signature. Like if we use the add function for an int and an int, it gets lowered at one point. Rather, let's look at the, I don't know, the format function for the value, which takes the value and then calls, I don't know, type info on the value and then switches over that. And if it's a struct, it does one thing. You know, if it's a, not bool doesn't exist, but if it's an int, then it's another thing. Like these kind of like if you compile format int, that would be one version of the function, and format of, you know, some struct, however that's going to look, that's another version. Yeah, so this will probably be a string, but it's more descriptive this way. Okay, so we have a map from only the functions, right? I think the definitions don't even need a map. Wait. Yeah, let's stay with functions for now, and we can still change that later on. So yeah, there's maps to yogurt. A yogurt fun. What's a yogurt fun? Well, it takes parameters, which are strings, I guess. Yeah. and maps them to a yogurt body. Which is a slice of expressions. And it returns a yogurt ID. That's also true. Okay. Yeah. The difference being that it also contains, instead of expression, let's maybe call it value. And it also contains types. So yeah, okay. I'm just realizing right now we have one flat body, and that works for a current code. But as soon as we have, like branches, for example with a switch, we need to have nested bodies still. That's quite a significant change. So I think I'm actually gonna implement switch right now already. Or am I? Nah, later on. We'll figure that out. So we have expressions, which is a slice of yogurt expressions. What's a yogurt expression, you ask? Well, yogurt expression has a value, which is a yogurt value, which is one of these. And it has a type, which is a yogurt type, which is basically, well, a type system. Yeah, we implement types. So yogurt type. What kind of types do we have in the language? I mean, currently, I think we only have ints. That makes the compiler fast and the type solving easy, because everything is an int. Every function just returns an int. But it does make things a bit too trivial, I think. Okay, so maybe we should add, I don't know, symbols or stuff like that before. Oh no, actually, when we say this is a global with a string, this add, for example, is a function. So there's also, a function, which is, plus we can say, fluke is add, and then we do that. So, you can store functions as well. Just saying. A fun, which is a, well, I don't know. It should store what kind of function it is. Maybe even the ast, or the name. Yeah, just the name of the definition. Yeah. Okay. Cool. Yeah, and then we can add symbols after that. But before, I think we could even compile this to like C or something. Okay, yogurt type. Beautiful. Martinaise. Let's implement. Oh, God. Yeah, not to yogurt, but we also need to implement the entire right thing. So first of all, this imports yogurt. Now. Is egg to yogurt. Which is yogurt. Beautiful. There are no definitions named to yogurt indeed. Let's change that. To yogurt. We have an egg. And we want a yogurt. So convert egg to yogurt. Beautiful. Yeah. Oh, by the way, this returns yogurt fun. Should pay more attention to, you know, what's hidden behind my face. Well. Okay, we have that. Cool. Now the last expression of this function returns the wrong thing. That is totally understandable. But before we do that, we want to be able to write yogurt. And I mean, this will be very, very similar to this one right here, right? Let me just take all the egg. Turn it into yogurt. And then go over the functions. And yeah, these are always functions. So we call them fun. Yeah, and they don't really have a name, do they? Well, okay, they have a key. Yeah, because they are map entries. Oh right, but this is a yogurt signature, so we need to say stop. Oh, okay, that's pain. That's yogurt signature. Yeah, okay, I guess that's implement right. Call signature. Yes, like this. Okay, a function has params. It does, yeah. But it's a map entry, so it's the function value. The value also contains a body. Beautiful. So then we can write those. Of course, there's yogurt. Yogurt ID. Yeah, we're sure. Colon is fine, I guess. Oh, wait. Colon is also a useful thing to write types in there. Yogurt body is the ID, basically, so let's maybe use an at or $. Let's use an at. We can change that later on. Yeah. Cool. I can even yogurt ID. just so that it's contained in here. Yeah, yogurt expression is not an enum, that is true. So we have an expression, the index, and then we're like, hey, by the way, this is of the type expression.item.type, and it is equal to the value. And let's maybe break that across multiple lines. Oh, by the way, yeah, the type can't be written. Strings in Martinaise work like this. You have double quotes, and when you do a new line, then the next line has to start with a single quote, and everything before that is just, you know, ignored. So it's a way to continue strings on the new line. Okay, right. So we have this, we have not this, but yogurt value. And then we should also do the same for types. Type being a yogurt type. So for ints, this will just be int. And for fun, that will just be, well, this is a function. There will probably be some payload in here, like the string, right? So the type is more like fun. Still, oh, by the way, fun. Yeah, sure. So how to convert them? This is where things get kind of tricky, to be honest. Because we basically need to have an entry point. You can't just compile the module. You need to know for which types do we need to compile this. So for example, if we have a main function that takes an A, we can like hard code in the compiler, please compile the main function for ints. And then the compiler will compile it, and if it calls other functions with, you know, concrete types, then it will compile those functions and so on. So that at the end we only have specialized functions, and we have all the functions that we need with types. Right, so I think it would need to be something like this. And I think I'm gonna remove this for now. Yeah, just do that. Maybe add 1 to A. So main takes an int, adds 1, and then returns the int plus 1. Yeah. I don't know how long I'm gonna code, because the weather is quite nice right now, and maybe I'll go for a walk. I probably will. So do I still do this? That's the question. Yeah, okay. The 2 yogurt, I'm gonna do that, but after that, that's it for the first coding session. Right, so, okay, yogurt type. Let's just convert them. I think we just go, we take the egg. Wait, we need to have like a function specialization or something. You know, in the egg we have functions, and we need a way to be able to say, hey, please compile this function for these types. So please compile this function for these types. And this should return a yogurt fun. Yes. Okay, that's pretty cool. So that in here we can say egg dot defs dot get maybe something called main. No main found. So you need to have a definition called main. And this should also be a function, to be honest. So main.fun or panic main is not a fun. Main equals stuff. And then main.params len should be equal to 1, or we're like, hey, main takes main.params.len params instead of 1. Yeah, and then when all of that works, then we're like, okay, let's convert this to yogurt. So main.toYogurt with types. With how many types? Well, a yogurt type, one type, which is int. So we call this, which returns a yogurt fun. And this should, it should also take, you know, something where it can save required other funs. Similar to how we pass the body around in the egg. Here we need to pass around the yogurt. And this will add required functions to the yogurt. I'm just gonna make sure that it doesn't, you know, flow over the line limit here. Okay, so converting a function to a yogurt. Yeah, that means that we create a yogurt here. Yogurt equals yogurt with funs, which is a map from yogurt signature to yogurt fun. And we pass that down here so that we can then return the yogurt. Nice. And what we do is we do something very, very similar to what we did in the ast. We create a yogurt body builder. Actually, let's copy this and then adjust that. A yogurt body builder, which has an expression, a vector of expressions. The index is the ID, and then we have a yogurt body builder with a vector of expressions. We can finish it to receive a yogurt body. Does that still exists? Yes. Yeah, finishing with the yogurt ID, wonderful. And then we can push an expression to the yogurt body builder, receiving a yogurt ID. Beautiful. So then, similar to what we do down here, we have a to yogurt, which takes I don't even know, to be honest. It takes a yogurt, no, an egg. Yeah, an egg expression. And a yogurt bodybuilder called body, and the yogurt, yes, and it returns a yogurt ID. Wonderful. A bit long, but oh, what are you gonna do? So then it switches over the expression, and it's one of these, which are not too many, you know, so that's fine. So if it's an int, then we basically add, you know, a yogurt expression here. Oh, and the yogurt expression consists of a value and a type, which is kind of pain to construct by hand. So let's create a new function. Oh, actually, let's create an operator. Something like, oh, can operators contain this? I don't think so. No. They contain $, $. Yeah, $. Let's create an operator that takes a yogurt value and a yogurt type and returns the yogurt expression. Yeah. What does it do? Well, it just creates the yogurt expression using the value and the type. But what that allows us to do is to say we want to push yogurt value dot int with the type yogurt type dot int. That's actually beautiful. Yeah, okay, I think this is not just gonna track the expressions, it's also going to save the types of parameters so that we can access them here. Basically, you know, like yogurt value dot param with a name, and the type depends on, you know, what got passed down here. And similarly, if it's global, then we push yogurt value dot global we switch on the global. You know, on the resolved global, kind of. Yeah. Oh, which means this needs the entire egg. Like, this function needs a lot of stuff. It needs, for example, if we have something that accesses a parameter with a name, we need to know the types of the parameters. We also need the entire egg, because this may refer to a global, which, you know, the whatever the global function does, it influences the type of this expression. So we need to pass a lot of parameters around. And I think it makes sense to refactor this to not just be a bodybuilder, but to be a yogurt, I don't know, fun compiler, maybe. You know? So basically something that only exists while you compile a function. And sure, it contains the body of the function. Yeah. but it also contains the parameter types. So maybe a map from name to parameter type. It contains the entire egg to, you know, look up things. It contains the yogurt mutably. So then we don't have this, and we don't really have a, you know, like this. We do have a push, but right. Cool. And then in here we say, hey, convert this expression to yogurt using this compiler. And then we also don't need this, which makes our code shorter. That's nice. Yeah. And here we can say compiler.params.get the parameter with that name, and we're guaranteed that it's there. By the way, get maybe would return an option, like a maybe, and get automatically unwraps that. So if it doesn't exist, then this crashes. But we know that the parameter exists because, you know, we created the ast and all of the. It only references parameters that actually exist. So then we have the global, and in that case we need to switch what is, you know, compiler .egg.devs.get global, which is guaranteed to exist. Well, for built-in functions we need to see how that works, but yeah, if that's a value, then, you know, actually what do we need to do in that case? This is like a purely functional language, so global values can't have any side effects, apart maybe from debug printing, because I think that should work everywhere, but not really side effects, you know. So I think we can just basically compile that value in here. Oh. So value to yogurt is what we're gonna do using the compiler. Yeah, if it's a call, then wait. We take the arguments of the call, correct? Yeah, we need to have multiple can fit the arguments, which is a vector of yogurt ID. We also have the argument types, which is a vector of types, and then for each argument in the calls and the call arguments, we need to compile each of those. So arg dot to yogurt. I think it's easier if this basically returns a copy or so of the expression. Oh, but then you don't have the ID. Right. Oh, this is pain. Kind of pain. Okay, it's the yogurt ID. This, and then you can say, oh, compiler.get with an ID would be super cool. You know, you can push things, you can get things. Compiler, in the yogurt fun compiler, you can say get with the yogurt ID, and you get back a yogurt expression, which is just compiler.body.get with the index, because the yogurt ID is just an index into the local body. Okay, so we can say compiler.get.type to get the type. And then we can say args dot push arg, arg types dot push type. Beautiful. And then we can compile the receiver I think we should do that first actually. So receiver is call.receiver.toYogurt. Yes. And this has to be a function. Yeah. So we can do compiler.get receiver.type is fun. You know, there's int and fun. Those are the possible types, and it needs to be a fun. Fun or panic called non-fun. Type. Oh, other way around. Yeah, type and then the type. Okay. Fun is, and let's maybe do this. Okay, so we have the function, like, you know, basically the name of the function that we want to call. We have lowered all of the arguments, and now we want to compile the function using the argument for the argument types, basically this right here. Yeah, so this only works on an egg fun. Yeah, so we need to get the function from the egg. Yeah, something like this, basically. By the way, I still need to handle this. Yeah, and here we need to basically do the same, but we know that this should be a function. Yes, like so. Okay, so we have the receiver or function that's being called, we have the arguments. And this is the function, or if it's not a function, then, you know, call the global variable. That's bad. Oh, well, actually, what if the variable evaluates to a function? I hate that. Maybe it makes sense to unify this thing in the ust already. You know, that if you refer to a global in the egg, I mean, if you refer to a global variable, not a function, then the variable definition could get like inlined into the function, so that there are not really any globals. The global values are just, you know, copied into the function. Yeah, so I'm gonna probably remove that, or to do. It's gonna be to do. To do don't have global variables would be one idea. Okay, so we have a function which is global, and then we have the arguments, and this is an egg fun. So then we can call this right here, egg fun dot fun dot to yogurt. For these argument types, yogurt is compiler.yogurt, and this returns a yogurt fun, I think. Yes, it does. And this is a compiled function, you know. It has this, this kind of function with a complete signature, with parameters, with a body. Could even have a return type here. Well, it's just, you can get that from the body as well, actually. So return type is fun dot body dot fun dot body, which is a body dot expressions get fun dot body dot returns dot int. Oh yeah. So yeah, that returns the expression, the yogurt expression that the body returns, and it has a type. So we've compiled the function, the required function, and we know its return type. And when we call this function with these types, we know that the type of this expression will be whatever the function returns. So we can say compiler.push, push a yogurt value, which will be a call of the function. Oh, how does it look up here? The receiver has a yogurt ID, right? Receiver. Sure. And then we'll have arguments. Oh, right. A yogurt call of that, like this. And the type of that is the return type. Beautiful. Yeah. Nice. So the only thing left is implementing this. And I mean, that's okay. We create a compiler. With an egg. Oh, well, I may refactor this, but I'm kind of getting tired or something. I'm gonna clean that up next time. For now, I just want to get this working, and then oh right. So params, yeah, is a map from string to yogurt type, and basically for e in args dot len, params dot put yeah, I know there's a zip method in the standard lib as well, but we're just gonna get the name from the eggfun params and map that name to the type that we're given. So then here we have the params, and the body is just an empty vec. Okay. Yeah, and then we say for each expression in the fun body is a body, I think so, we lower that. Yeah, we're gonna care about that later. We're gonna call expression.toYogurt using the compiler. Please compile that. Nice. And in the end, we create a yogurt fun and return that. And the yogurt fun has, what was it? Params and a body. Params is basically the egg fun params, and the body is Do we still have the finish function? No, we don't. Well, the body is a yogurt body with this a list of expressions, which is the compiler dot body to slice, I think, and a return value, which is the last expression. So we need to track that as well. Right. So this will be no yogurt ID, and then here we'll say that we set that, and here it's last or panic fun with no body, also known as without body. So in here we can say returns is last. Yes, something like that. Let's compile that. Okay, we compile a yogurt fun, an egg fun with yogurt. Oh, and we need to pass in the egg as well. Yeah, makes sense, because the function can't be compiled in isolation. It needs to be able to inspect and compile other functions. Right. So what's going on here? Iter on a body. Probably because the body contains expressions or something. Yeah. Okay, so this is not in scope because this is the compiler. Indeed. Value.toYogurt doesn't work because it's an egg body. Oh. An egg body. Why did we have an egg? Oh, the global thing, yeah. Yeah, I think I'm gonna replace this with a to-do. Yogurt expression. Okay, yeah. To-do never returns, but this, like, the compiler should allow this, I believe. But okay, sure. Maybe. I mean, we still have to do the fun thing right here. If we have a function, then we want to compile that function. So function.toYogurt. Oh no, we actually want to, we want to emit something entirely different. We want to emit a yogurt value dot global with the function name, right? Yeah, I think we don't even need this. Or do we? Maybe we do. Global with egg fun, but it needs a string. Indeed it does. Yeah, like this. And the type of that is yogurt type dot fun with the fun name. So that's just global. Okay, yeah, we turn the receiver into yogurt using the compiler. Hang on, this doesn't work because it's an ID. So we need to get the corresponding expression for the ID. Of course we do. Of course we do. But the yogurt fun compiler can contain the egg fun as well. Yes, then we need to egg fun is fun. Oh. And then we can say take the receiver, compiler dot egg fun dot body dot get, call that receiver, which is an egg ID or something. Doesn't work because this still contains expressions or something. Yeah. This is horrible, but you know, refactoring is, we can do that later. Before refactoring all of these, you know, very hacky things, I first want to settle on an architecture. And like, for example, the global values, this is gonna get removed anyways. So I'm not too sad about having like temporary code in here. Okay, global is not in scope. Why is that the case? Because we want to get the global, but of course it's called fun, maybe? Oh yeah, it's called fun. Okay, we compile the argument. Doesn't work because it's an ID, of course. Okay, you know what? Maybe I'm gonna add a compiler ID, please, which just does this. Not even 1 minute after I said this, I'm gonna not refactor this now. I'm refactoring it. Well, that's receiver dot to yogurt, and this is the ID. Now turning an ID into yogurt, gets the expression and returns that into yogurt. Beautiful. And turning a fun into yogurt also needs, not this, but needs an egg. Yes, I can have that. Okay, yeah, yogurt type, this should be a slice. Sure. Beautiful. At least kind of beautiful. Oh, wow. Yes. So built-in add doesn't exist, and that makes sense. Ah, that is so cool. That is so cool. Yeah, let me maybe, instead of doing this, add is just going to return a. What? Okay. Cool. Yeah, why is nothing being printed? That's kind of sad. Oh, but I know why. Because we never add a function to the map. So in here, when we say, hey, please compile a function, then we have the function. And yes, we want to return that, but we also want to add it to the yogurt. So yogurt dot funds dot put. Yeah, the signature. We still have to build that, and the function. What's the signature? Well, we have these. Is we need to find the signature. Like, what's the signature? Yogurt signature. Yogurt signature created using the, you know, the name of the function. Which we don't have actually. We don't have the name of the function. That's crazy. Like, that's super crazy. well, okay. Also needs, yeah, let's put it there, the name. So have the name and the args. And then we create a, you can create a yogurt signature using a name and archetypes. But in reality, the signature is just a string, so it just concatenates stuff. And actually there's a string builder, store builder, just for that, where you can say, hey, I want to print the name, and then for type in archetypes, I want to print a space and then the type. Yeah, something like this. Oh, right, and then wrap that in a yogurt signature. Cool. So down here, we can say, we also need the name, which is main. This call doesn't work. Sure. Why not? Egg fun. Oh, because it's the other way around. Yeah, that makes sense. Cool. So then up here, there are no definitions called store builder. That's... Oh, right. Let me just... like pull the newest changes from Martinaise. And now it works. Wait. Yeah, before it was called string builder, and I recently changed that in the standard library. Okay. Oh, not okay. What did I do? Well, where's the mem module? Why isn't... Okay. Well. Set lib mem. Wait, where? Martinaise standard lib mem. Line 372. Oh, I see. Yeah. So if you have a string with string interpolation, then it automatically uses a string builder. Or it used to. Now it uses a store builder. So I actually need to... Yeah, I recently changed that, so I'm just gonna make Martinaise, which compiles... there were several stages, and each compiler can compile the next compiler. So Martinaise 6 is used to compile, Martinaise 6 is used to compile Martinaise 7. Now 7 is used to compile Martinaise 8. And 8 is, I think, yeah, the current version. Oh, right. So this should not work. Perfect. Well, it doesn't work, but because of other reasons. Oh, right. Down here, we also need to pass in the name of the function, which, if I recall correctly, is fun name, I'm gonna call it. And then in here I can say to yogurt fun name. Okay, yeah, now we're getting somewhere. So we have a map of yogurt signatures, which means that yogurt signatures need to support equals and hash. So yeah, we're gonna implement equals for yogurt signatures. So we have two yogurt signatures, A and B, and we can just check if the strings are equal, yeah. And hash takes a hasher and a signature. Well, yeah, and it's just a hasher.hash signature.store. Okay, let's keep it short. Okay, so now we can use those as map keys. Oh, look at that. Look at that. So here we have, okay, yeah, we also only have two functions, but you know, we have the main function, which takes an int. What? So then we have this, you know, we have a parameter a of type int. We have a global add, just like we did here, but the type of that is, this is the add function. Like, you know, a compile time known function is what this is. And then we create a one, which has the type int. We take the global add again, because I don't know why. And oh, that actually, it seems like something is evaluated twice. Then we take the parameter again, and then we call things. Yeah, that kind of seems weird. But let me make a quick break. I mean, this is weird. Yeah. And I'm back. Okay, so where were we? Oh yeah, some expressions were there multiple times. Like, you know, the parameter, the add, the int. And I don't know why. So we have a function. Oh. Oh, this makes sense. Yeah, we just go over all the expressions. Hang on, when we have a... Oh, right. It shouldn't be like this, right? We go through the function line by line. So by this point, the receiver is guaranteed to already be compiled into yogurt. We just need, I don't know, a map from egg to yogurt, which is a map from an egg ID to yogurt ID. And yes. Okay, so then we'll probably have a lookup of an egg ID, and it returns yogurt ID on the compiler. So compiler egg to yogurt dot get egg ID. And when we compile an ID, yeah, we create the yogurt ID. Oh. Do it like this. And then we say compiler.egg to yogurt dot put egg ID. Yogurt ID, and then we return the yogurt ID. So when compiling these expressions, yeah, we have to do this, but we never have to call toYogurt on something. Instead, well, for the function, yes. Yeah, this down here, we have to do that. But for other expressions, never. We can just say compiler.lookup, and this gives us yogurt ID. And similarly here, the function we can just, in the arguments, we can just say compiler to look up the argument. Yes. Okay, so true. Why isn't it showing in the IDE? It's kind of weird, right? That's super weird, actually. Yeah, we create that here, and egg to yogurt is gonna be a map from egg ID to yogurt ID. Oh, right, of course. Egg IDs also need to be able to be hashed. So let's fix that. So we want to be able to equate one egg ID or compare with another egg ID, and that should return a bool if the ints, the underlying ints, are the same. Same goes for hashing. We just hash the underlying int of the ID. Okay. Look at that. Okay, so egg ID 1 is not in the map. That's a problem. That is a problem. Yeah. Why is that not in the map? When we compile a function, which is exactly what we do here, we go over all of the expressions. Oh. And then return the expression to yogurt instead of an ID matching the expression. Yeah, so let's maybe do this instead. ID is an egg ID, an int, which is the index. So then we say, hey, ID, compile yourself to yogurt. And this should also add things. Yeah, look at this. Now we have the parameter A, we have the global add, which, you know, has the type fun add. We have an int of type int. And now we call this add function with an int and another int. Which means now it goes and tries to compile the add function, this one right here, to an add function that takes an int and another int. And it sees, okay, this is an int, this is an int. It returns a, which is also an int, which means the result of this call is also an int. That's pretty amazing. I mean, it's not that amazing because nearly everything is an int right now. But, you know, if we support more types, then the functions get compiled for those specific types, and they get, you know, they evaluate to that type. That's pretty cool. Right. I think that's it for today. Okay, one tiny addition I'm gonna do. So there's an int type, but what about if types, if individuals are also types? Like for example, if you write 4 equals 3, the type of this is int. But what if the type of this was 3? That would be cool. That would be super cool. Because then, you know, if you compile add for int and 3, it still contains the add. But if you compile add for, I don't know, 2 and 3, for example, then the type is something else. The type of that is 5, while the type of this is int. I think it would be nice to have this, like, you know, constant folding by basically just having comp time ints be their own type. So something can have the type 5 or the type 1. That's pretty amazing. Yeah, let's do that. Let's do that. Let's add a type called comptime int, which contains the actual integer value. So it doesn't, you know, at runtime it doesn't even need to exist. That also means that this doesn't need to exist. Because really, we could just say, well, this is a, you know, something that's known at comp time. And that's it. What? I mean, that's kind of... Wait, do we even need this? Because the only way we're creating that, yeah, is for functions. And the type of that is already the function with the concrete function name inside. So I think even this we don't need. That's strange, but I think this works. Yeah, let's try to do that. So in particular, let's just, you know, if you compile an int, then instead of having this int value, you have comp time as a value, and comp time int with the int as the type. Similarly here, this will just be replaced with comp time, yes. And now, well, we can't write those types, that's true. So yeah, we have int and we have comp time int, which is just going to print the int. Oh right, and for the value we don't have this, but we have comp time, which is just going to print comp time. Okay, that's it. Oops. Oh, look at that. We have main, which receives an int. and it has a parameter a of the type int. Then it has this right here, which is, exists only at compile time. Doesn't take up any space in the, or it doesn't even need to do anything in the final execution, because this is just the add function known at compile time. And then we have this compile time value, which is of type 1. And here we call the add function with a compile time 1 and a runtime known int, which means that the add function gets specialized for a 1 and an int. Yeah, which means we have a parameter a of type 1 and a parameter b of type int. That's crazy. And it returns 1, so it returns an int. So the result of this call is an int. And the main function returns an int. What? That's amazing. That is super cool. Okay. We're getting into that, comp time area where things get really, really kind of mind-bending. Having the type 5. That's cool. I like it. Hang on. We have A and B, and it results in the first thing. But here it returns 1. That doesn't seem right. That doesn't seem right at all. Oh, and I know why. Because at some point we use last, yeah. And we shouldn't. We should just create an ID, compile that to yogurt, and just ignore the result. And then the last thing, or rather, it returns, well, compiler.egg to yogurt, getting from the body dot returns. Yeah, this is correct. Now add of 1 and int returns 0, which is the 1. So yeah, the return value of this call is 1. And the main function always returns 1. So it ignores the input, basically. That seems correct. Okay. Let's maybe review what we did. So I'm gonna switch back to that thingy, to this one, because we already achieved quite a bit. We have source code, which gets converted into an ild currently. Name is gonna change to some breakfast thing. Ild. And then that gets transformed into, what was it? Toast, of course. So we have toast. And then we turn this toast, which just represents the structure of the program like you wrote it in the file. We resolve names and so on. And that becomes the egg, the expression guided graph. Boom. And then that egg becomes, what does that become? Here, the yogurt, of course. And here we have types, you know. Source code is just a file with characters inside them. Then we pass the indentation, we turn that into a syntax tree representing what we wrote, we analyze that, resolve names, flatten the instructions out into a single level, then we find out the types of all of the expressions. Yeah, I think we made good progress. The next part would be to kind of go on from there. Think about what next stages. What would the next stages be? Probably already compiling to something like C, right? I think you could do that. Yeah, probably you could do that, yes. But you can't really express any useful code in this. So I think before compiling to C, it would make sense to introduce symbols at least and switches, because then we have some kind of control flow. Yeah, but that's not for today. Okay, cool. So, oh, I should probably publish this to GitHub. Okay. Yeah, I just published the thing to Git. Yeah, it's, hang on. So we have there's a repo now with build, toast, egg, and yogurt. I mean, for like 600 lines, that's not a lot of code, but we have like multiple compiler stages and everything. So I think we made some good progress today. We have a nice representation with types, everything, names resolved, expressions flattened. I think that's a nice place to be. Yeah, next would be adding symbols and switch, but yeah, for now, for today, we're done. And I guess I'll leave you with this cool image and see you next time. Bye.